Hi, Maria. Good morning, everybody. Good day, everybody. I'm going to unmute myself. Can you hear me?
Yes, we can hear you. Thank you.
Okay, great. We're a very quiet group. Yes. Hi,
It's either
Jingyi.
too early or too late.
That's right. I'm in the kind of best time zone, I guess.
Ah, lucky
Yes.
you.
So, Jingyi, how are you today?
Morning
Good
and good
morning.
afternoon, everyone.
Yes. I see Dennis is here. And let's see. Dr. Giro. That's a good photo. Valentino's here. And of course, John Vinson. How are you, John? I guess you're in Germany now. Yes.
Not quite.
Oh, not quite. Okay. Are you? But I somehow thought there was a Germany trip for you sometime.
Yeah, not until tomorrow.
Oh, tomorrow. Okay. I see.
I thought you meant spatially, not quite, not temporally.
Oh,
I was like, where could you be between here and Germany?
On an
cool.
airplane, I guess. Yes.
That would be amazing.
So, John, I only heard Germany. Which specific city will you be in?
I'll be in Karlsruhe, so
Okay.
the southwest.
Okay, great. Yeah. Are you all packed?
Oh, pretty much, except the computer.
So, Dr. Giro, could you unmute yourself and teach me how to pronounce your first name? Demuraya, is that correct? Demuraya. Demuraya. Okay. Jing is coming. She's coming. So, Latifa, I haven't reviewed the registration sheet. What city are you joining from today?
Yes, hi.
Hi there. Where are you joining us from?
Yes. Yes, I'm from Saudi Arabia.
Oh, okay.
Yes.
How are you finding the workshop so far?
Yeah, it's so helpful and it's very close to my study in the master degree. And I don't know, maybe yesterday I hear if we can, how I can say, get in touch with the sponsor here. So I don't know.
Oh, let me put my email address
Yes.
here. Yes, so that you can contact me. And so this is my university address. Oops, let me put my university address here. And then my USAfri, Africa, I hope I don't make a typo. Africa Initiative at gmail.com. Yes, so that's the other address. So anyone is welcome to contact me at either of those addresses. If you would like to talk to any of the other attendees or the other speakers, just let me know and I'd be more than happy to put you in contact with them. And let's see what else. Also, I
Thank
don't
you.
know if you're familiar. So I'm glad you're here, Latifa, and I'm glad you mentioned that. Thank you. I also wanted to mention, let me put a link here to the, in case you haven't heard about the electronic structure workshop next week. Have you heard about that, Latifa? Are you registered for that? I didn't look at the registration names for that workshop. So I put a link in the chat there, and I believe registration is still open. Yes, so registration ticket, it'll be called registration ticket number 5, and that's the virtual participation. So everyone can register for that still. and you will recognize some of the same participants, but they of course have a different list of speakers. Let me just post that in there. You can see some of the speaker names. Oops. So, yep, here's the first 8, and then here's the next group. And then yes, so those are some of the. Hi Mbusa, nice to see you. So those are the current talk titles, and those are the lists of the speakers for next week's workshop. It's also Wednesday, Thursday, Friday. And that is also, you'll recognize Jingyi will be there. And several of the other helpers that she's arranged. Yes, so you'll be able to join on those talks. And Jingyi, I believe those will also be recorded. Is that correct?
I think so, yes.
Yeah, I think those talks will also be recorded. So if the time zone doesn't quite work out for the whole day for people in different time zones, you can still catch many of the recordings. Oh, great. Yes, so we'll be happy to see you there. I see Isaiah. Hello, Isaiah. Good to see you there, Sasen. And Fatima is here. Very nice.
Yeah, I'm here. Thank you, Amy.
Nice to see you. Great.
Thank you. Yeah.
Uh-huh.
Hello. Good
Hi,
afternoon.
Isaiah. Hi, Isaiah.
Yeah.
Hello, afternoon. Where are you joining from? I didn't look at the sheet, so you might have written that down, but I don't have the sheet in front of me.
Joining from Nigeria.
Oh, okay, great.
Yeah.
Who else is in your research group? Do you know other people at this meeting?
Not really.
Not really. Oh, okay.
Yeah.
I'm glad you're here so that you can hopefully meet some more people with your interests. What's your background?
From mechanical engineering. Then in my graduate study, I'm studying energy materials towards a solar application.
Oh, okay, terrific. Well,
Yeah.
we're happy you're here. I hope you're finding the different talks and discussions useful for your research.
Yes, indeed.
Great.
Yesterday's topic was tailored to what I'm researching on, the perovskite
Oh,
materials.
okay. Oh, great.
Yes.
Nice. So I'm so glad you're here. Let's see.
Yeah.
Oh, okay. Thank you. Thank you for
Uh,
telling us about yourself.
Yeah, it's a pleasure.
So, John, how are you doing? John Vinson and Steve, how are you doing?
Oh, I'm good, Amy. Hi.
Good. Good morning.
Morning.
And Steve, you said it's sunny in Kigali, but it's raining where Michel Cote is in Montreal. Although I must say, you know, in Champagne, it can rain and then it won't be raining in Urbana. So if you've been to Champagne, Urbana, you know that's what it's like here. Okay, let's see. I see Sinéad and Jingyi. By my clock, it's 8 o'clock. How are you feeling with the time?
It's still pretty early.
It's still a little early? Okay. So we should not start yet? I think, let's see. Let me look at this.
I think more people is coming.
I think so too. I don't want I don't want people to miss. So let's see. Steve, let me go ahead then and ask you, will you do you plan to post your talk slides after your talk?
Yeah, maybe.
Okay. You don't have to. I just was wondering if you want to, I can post them. But if you don't, no problem, of course. Okay. Is it okay to record them? To record your talk then?
Sure. You can
Oh, okay.
record it. Yeah.
Okay. And Maria?
Recording in progress.
Okay, great. That's
Yeah, it's fine with me. Thanks.
great. Okay. Yes. I have two Fatimas. Fatima's here. Fatime Amerik Harabadi. Good to see you. Okay. Yes. And Sinéad is here. What would you like to do, Steve and John? Would you like to wait another couple minutes?
I'm okay with everything, so all good for me.
I would say start.
Yeah.
Okay.
Is that all right? Does anyone object if we start?
No, I think it's fine.
Okay.
Oh, excellent.
Okay.
That looks good.
Mm.
We can see your mouse.
Okay.
All right. So my name is John Vinson. I work at the National Institute of Standards and Technology here in the US. We have 2 invited talks this session, so people can put questions into the chat, or after the talk, use the raise hand function and call on you. First up, we have Steve Ndengué, who's a senior lecturer at the East African Institute for Fundamental Research in Kigali, Rwanda. And today he will be telling us about quantum dynamics of the water dimer. So please.
Good morning. Thank you for the introduction. As it was said, I'm Steve Ndengué. I'm a senior lecturer at the East African Institute for Fundamental Research, which is based in Kigali, Rwanda. I'm very appreciative for the opportunity to be talking about some of the work we've been doing here at IFA. It's in no way an exhaustive list of what we are interested in. Our domain of interest range from electronic structure to molecular dynamics, quantum dynamics for application in catalysis, atmospheric chemistry, astrophysics. So it's a very broad domain of area, both in my research group, but also in the condensed matter group as a whole. I would like to thank Columbia University, USAfrI, and APS Physics through the Innovation Fund for giving me the possibility of presenting this work. Thank also the host in the US, that's going to be Prof. Nipa Mitra from Rutgers. I had the pleasure of meeting her last year, and we had very interesting discussion already. So I'm looking forward for our next meeting. So this session is in principle about quantum materials, but I'm going to be a little out of it. I'm going to talk about something that we really much appreciate in our research group, and I'm going to talk about water. And I'm going to talk about some quantum dynamic simulation that we've been doing on water for the past couple of years. And I will try to walk you through the project as it is and why we were interested in those type of questions at this time. Okay, so first of all, water is very present in our everyday life, and the study of its properties in all type of phases are one of the main goals of chemical physics in the past few years. In particular, the study of the properties of aqueous properties are important in chemistry. They're also important in biology. But most of the time we use gas-phase studies as very important in order to understand molecular interaction, which are thought to be essential in understanding important features in the condensed phase. So most of the time people start working on the water dimer and work their way up until hexamer and even bigger cluster. And what we are really much interested in is understanding as the best way possible using very high quality numerical techniques. Our interest is at the beginning fundamental besides the potential application, but what we intend to do most mainly is to get some deep understanding in the processes, get some deep understanding in what are the main ingredients that generate the properties or some features that we observe in the spectrum or in the system of interest, with the goal of being able to have some predictive possibilities and even some engineering and design probability opportunities using, for instance, quantum control, which is something that is trending a little more recently. But all of this relies on how well we can understand water, how well we can understand the origin of the features that we see, for instance, on the spectrum of water. And this is what actually one of the goals that we try to follow here, not just on water, but on several systems that we are studying. So how did we come around this specific project? So about 2 years ago, there was a new instrument that was designed in China, a new laser. And the hope they had used on that laser was to be able to obtain to a very good, I mean, probably the best accuracy so far, the spectrum of water cluster in the range of the OH stretch. Now, the issue with this specific type of description is the fact that we are not actually the issue with this specific type of description is that water, when you try to measure water, for instance, specific water cluster, the preparation of the sample is very essential, and there is a high chance of having some pollution of bigger water cluster. So they made some measurement of that specific water cluster, and that's the picture that is shown here. So they excite the water dimer using a laser, and they record in the OH stretch band some of the motion of the water cluster. Using quantum chemical calculation, later on they made some assignment of the various motion. For instance, the peak on the right here is the antisymmetric OH stretch of the acceptor. The acceptor is this specific molecule that can accept a proton. So this is the antisymmetric stretch of this water. The second one is the OH, the B structure, the main one here, should be, the way they assign it should be the B free OH stretch. That is of the donor, that is this specific motion that you can see here. The C will be the symmetric stretch of this acceptor, and the last features that they claim to be here should be the OH hydrogen donor bonding motion. So they made this assignment using some quantum chemical calculation, as you can see in the table, but overall, they were not satisfied by these results. They were not satisfied by the discrepancy that you can see between experimental calculation and experimental measurement and the calculation. But moreover, they were not really, they were not able to explain clearly where does these triple features that you see about above 3700 wave number comes from. So that's where we came into play. So they contacted us. By us, I mean a group of researchers. Some are based in France, some are based in Germany, and us here in Rwanda, to try to use a very efficient quantum dynamical simulation to be able to assign all of these features without any ambiguity. And specifically, they were expecting us to validate their experimental result and explain actually the origin of this triple structure that you see in this range of the spectrum. Well, in the meantime, this type of work became interesting, and we started a calculation, and actually we first noticed something that was not quite right. And in the process of going through the literature, we found this paper that was actually published last year, where they tend to disprove the assignment that they made on that specific system. Specifically, they claim that the feature that was supposed to be observed in this range is not actually the water dimer, but it's more like the water trimer. But in addition, they assess that there is some spectrum, some band that is supposed to appear in this region that unfortunately is not visible. So that's what this paper claimed. So also, already we had some kind of controversy. And when we go into the literature, we realize that for the past decades, this has actually never been resolved. There have been many work, for instance, the work from David Coker, that tend to follow the assignment that was done by the Chinese group. And there were other works, for instance, this work by Kuyanov that tend to follow the second type of assignment. So we were more like in the middle of something, and we tried to say, okay, let's try to use simulation, let's try to use calculation to provide a definitive answer to what is going on right here. Also, a few weeks ago, another group did some time independent calculation using a reduced dimensional model, still on the water dimer, and they more or less found results that seemed to be in good agreement with the work from last year, and not from the assignment that was made initially. So globally, there are actually two main things that one has to understand. The first thing is that, the first thing is that first, the assignment of these two bands was already made and was already correct, accurate, approved by everyone. But the assignment of this feature that they seem to see in their spectrum, there was some discussion on what is actually going on in this region. And that's actually what we intended to do. So this work is not completely finished, but we already have enough information to be explained, to explain what what we can understand from the water dimer in this specific OH stretch region. And what we gave ourselves as a task was first to be able to assign correctly the bands that we can see on the spectrum between 3500 and 3800 wave number for that specific system. And secondly, to be able to explain the origin of this specific set of this triple structure that we see in this area. And for this purpose, we decide to use a fully quantum mechanical approach that is starting from the electronic structure on going to the dynamics. For the electronic structure, we use a very high level of theory that is likely of chemical accuracy. For the dynamics, we use also a very improved quantum dynamical approach to be able to describe the dynamic of the system. It's actually a wave function approach. I'm going to describe it in the next few slides. After doing the dynamics, we do some post-treatment analysis of the dynamics, and we are able to understand very clearly what is actually going on in this specific area. So this is not finished yet, but as I said, we already have enough information to explain what we are seeing in this spectra. So first, let me talk about the quantum dynamical method that we use for this specific purpose. So let me start from the beginning. And at the beginning, we start with the Schrödinger equation for the electron and the nuclei. So this is how I describe all the Colombian interaction between the electron and the kinetic energy. Now, if you use the Born-Oppenheimer approximation, which we quite often do, you are able to separate the motion of the electron from the motion of the nuclei of the system. And now you are able to solve only the Schrödinger equation for the electronic motion to obtain the electronic energy. That most of the time what we do is that we interpolate them or feed them into what is known as a potential energy surface. So for this specific work, we use a very high level of theory, that is the coupled cluster single of double with perturbative triple. We are able to do that because we are dealing with a system that has a relatively small size. And this type of calculation are expensive, but not too expensive. And the benefit is that we have a very accurate potential energy surface on harm, which has a predictive character. Now, using that potential energy surface, we use it as an input to run the dynamics. If you were to do the classical dynamics, that potential energy surface is the parameter from which we extract the forces that we use to follow the classical dynamics. In our case, we still follow the idea of the Schrödinger equation, and we try to solve the time-dependent Schrödinger equation for this specific problem. And the crude way of doing it, the simplest way of approaching this problem is simply expanding the wave function that depends on several degrees of freedom on a basis, a time-independent basis, as it's written in equation 3. We add the coefficient C at the time-dependent coefficient that allows you to follow the motion of the wave packet, because in this case, we are dealing with a wave packet throughout the dynamics of the problem. This is appropriate because we are dealing with system with small size, small size like the hydrogen atom. So we really need to have the quantum character showing up in the description. So the next thing, now we take this kind of wave function ansatz, we plug it into a a variational principle, and we are able to obtain the propagation equation of motion for those coefficients. So we are able to follow the dynamics of the system. One thing that you notice when you look at equation 5 is that you have to at some point to deal with some very complicated multidimensional integrals. So if you have many atoms in your system, this kind of integral become very heavy to calculate and very cumbersome, and the main limitation in the dynamics. A practical case, if you think, for instance, of solving the nuclear dynamics of some simple molecule like molecular hydrogen or methane, which has like 5 atoms, the degrees of freedom of the system are actually depending on that formula F equal to n-6. And you have to deal with matrices of size that are exponentially big. And that type of issue is a very well-known issue, not only in quantum dynamics, but in many other fields, also electronic structure, where you have to deal in some way with the size of the system. And that kind of exponential scaling is the main limitation in using the rough approach to solve the problem using quantum dynamics. One possibility of going around that is what has been done so far a lot is using those approach both based on the path integral formalism. And you have those methods like ring polymer molecular dynamics, central molecular dynamics, but that's not the type of route that we try to follow here. What we try to is to use a full wave function type of method, and you are going to see later on why we favor this type of method. So if we don't want to follow this path integral formalism, the alternative is to still try to solve the time-dependent, the Schrödinger equation in the time-dependent form. So one possibility is to use some kind of Millfield treatment of the system, and that brings you to the time-dependent Hartree formalism, where you actually write your wave function in a different way. You simply write it as a product of one-dimensional function as it's written in 6. So those wave functions are likely to evolve as you evolve through time. And then you can apply again a variational principle, and in the end you get equation 10 that gives you the evolution of those one-dimensional wave function through time. Here you are dealing with low dimensional integral, and therefore the calculations are much more easier, and you can easily increase the dimensionality of the problem with less issues. The real problem about this Millfield type of formalism is that you are losing a lot of information because there is no correlation in the description of the problem. And for that reason, this type of method is most of the time not very reliable when you have to solve in a serious fashion the dynamics of the system. A better way of doing this is to think about including several of these type of Hartree determinant that is going into a multi-configuration time-dependent Hartree formalism. And this method was actually developed about a little more than 30 years ago and has been very efficient. So the idea here is that if you have to write your system represent it in the Hilbert space, because most of the time you know that the dynamics is going to be local, or instead of choosing a basis that is going to span the whole Hilbert space, you can choose a very restricted basis that is going to evolve through time, and that is going to follow the dynamics. With this type of method, you need just a very small number of functions to follow the dynamics of the system, and that makes the computation much more affordable. So in this way, you then write the wave function as it's written in 11, where you write it depending on a set of coefficients that depends on time, so that they will be evolving in time, just like the first method we presented. And also your function have the same spirit of the Millfield function in the sense that they are also evolving in time. So that's your basis that is actually moving with the Wavepacket with the system as it explores the whole phase space area. Again, applying the variational principle, in the end, you get 2 sets of equations, one for the coefficient as it evolves through time, and one for the function that we call single particle function that also evolving through time. So what is the benefit of using that type of method? So you can see it in a clear type of example. If you think, for instance, of using, let's say, 32 grid points to describe the whole phase space for each specific degrees of freedom, so for each specific direction, you decide to use just, say, let's say 7 functions for each of these degrees of freedom, you realize that the memory cost, as you increase the number of degrees of freedom, increase much slower when you use that specific method, MCTH method, compared to when you use the very first method that I showed you, which is called what which is often referred to as the standard method for solving a problem. So you have a reduction in the cost in the dynamics that you are studying, but that reduction in cost is also transferring the amount of the type of calculation that you can do. So you are able to explore bigger and bigger systems using this method, but also it's much easier for some smaller system to treat. And even on your small laptop, you can think about solving some problem that you were not able to do even on some specific cluster. However, you can see that as you increase the dimensionality, there's still this kind of exponential increase in the cost of the calculation. And that doesn't disappear when you use the MCTDH method. It doesn't disappear altogether, but it allows us to do a little more than what we would be able to do in a separate context. But as a matter of fact, this type of method is not an outlier. It's just a set of methods that are being more and more being developed these days. And the method that I described to you, the MCTDH method, is often referred to as the Tucker formalism for people in the mathematics field. And this is how it's graphically represented. This type of method, you can see it as a contraction type of method in the sense that if you take an image and you have it in high resolution, if you perform some contraction and you use a lower resolution, you still can see essentially the image that you want to see. You have the essential part of the information, even though you miss some of the details. And it's actually the same type of idea. So you can think about this type of method as a contraction method. And this level of this contraction, you can actually think of applying at several levels. So you can perform several layers of contraction and making the system more and more compact. And that's what's shown is this later graph, which is referred as multi-layer MCTDH method. Another name that is being given in the mathematical area is hierarchical Tucker method. It's interesting to realize that this hierarchical Tucker method is actually a generalization of the commonly known method as tensor train, metric product state, or DMRG. So all these set of methods are all part of big group of techniques that are called tensor-based network algorithm and method that are the topic of research of several research areas these days. So this put aside, this gives you just an idea to show you that this type of approach are very powerful, very efficient, and allows you to go a little bit further than what has been done so far, whether it's with respect to quantum dynamics, but even with respect to electronic structure calculation, as the DMRG, for instance, has been used more and more to deal with electronic structure problem. So now if we go back to the problem in hand, when you have to solve the Schrödinger equation for the electron, what you actually fall into, the main difficulty that you encounter is the representation of the Hamiltonian. And it's very essential when you run this type of calculation to have your Hamiltonian expressed in what is known as a sum of product form. And the sum of product form is simply an equation that looks like 17, where you expand your Hamiltonian as a sum of product of low dimensional operator that could be of dimension 1, 2. And the goal is that because we have to perform multidimensional integral at some point, it's better to have to do several one-dimensional integral instead of doing a big multidimensional integral. That allows you to save cost and save memory space altogether. So this task of transforming the Hamiltonian into that sum of product form is more or less easy when you talk about the kinetic energy operator. There are some software that are available once you decide of the choice of the coordinates that you want for the dynamics. This is the one that we selected for the water dynamics. You can use some software to generate you an Hamiltonian that is already in that sum of product form representation. Sometimes there are several numbers or several terms that are involved, but the program works well and is very flexible and adaptable to the needs that you may have. The main difficulty actually comes into play when you have to deal with the potential energy surface. Here you have a multidimensional surface, and most of the time they are not produced in the set of coordinates that you would want to use for the dynamics. So you have most of the time to do additional transformation. And even if originally you had something that could have been in the sum of product format, in the end you may have something that is extremely complicated. Some kind of very tricky potential energy surface that come into play these days are those kind of machine learning potential, which are extremely complicated and actually not in the sum of product form for any dynamical simulation. So there are also some software that are available to deal with this type of problem. They are not as robust as the one that generates a kinetic energy operator, but they are also an active domain of research. The one that we used for this specific work was called MCCPD, which is a Monte Carlo CPD approach to represent the potential in a very compact form. And here you can see, for instance, the cut of the potential, 2 degrees of freedom of the potential from the original file, and how we were able to fit it and represent it, transform it into that specific small product form for the dynamics. So you see the two results match extremely well and give us some trust in the quality of the result that we are going to obtain later on. Okay, so basically, this approach that we are using, it's some of the advantage that it's cheaper than the standard method, as you see, but it's still more expensive, those path integral techniques that are based on classical trajectory for obvious reason. Most of the time, when you can run these wave function-based calculation, they are thought to be more accurate than path integral simulation, and they are used quite often as benchmark to validate all the other path integral quantum mechanical simulation. The benefit of the MCTH method, as I'm going to show you in a few slides, is that you get the wave function, and that allows you to perform a deeper analysis of the dynamics. It allows you actually to follow the packet, the system as it's going through all the stages of the problem. And that problem of the exponential scaling is an active topic of research, both here in Rwanda at various other places where we are thinking about ways of solving the dynamics of the problem and using those ideas of contraction to make the calculation more affordable and testing on some case problem like this one. So now, going back to our initial question, how can we obtain the infrared spectrum of the system? So the first thing we need to know to do is to prepare our system in its initial state. So without any external effect, any external perturbation, the system is likely going to be in some of its lowest state. It's in its ground state. So to prepare the system in the ground state, what we often do is to perform a wave packet propagation, and the wave packet is going to coalesce directly into the ground states, the lowest state of the system. Now, using that initial state, we can apply a dipole moment surface, dipole moment on it that comes from the effect, whether it's the laser or the field that is applied on the system, and follow then the dynamics of the system for a specific amount of time. For this specific study, we follow the dynamics for about 5 picoseconds. And after following the dynamics, while following the dynamics, we record the autocorrelation function, and the Fourier transform of that autocorrelation function actually gives us the spectrum that you can see here. In this slide, I compared the spectrum that you can see on this part with some experimental data from 2010, where we actually see some of the same feature. The structure at 3600 is the BD that you can see here. The highest peak is the FD that you see here, and there are 2 features here, but in principle, we observe about 3 in that range, just after that specific feature. And below is the same experiment where they allow the system to be in contact with more water, and right away you see that that feature that is N becomes significant, which is due to some pollution of the sample for that specific work. So what can we do? So what can we do now from this simulation? I'm going to skip this slide. What we can do with this specific simulation is that we can get information about what is going on in the problem. So once we prepare the initial wave packet and we allow the propagation for a specific amount of time, we can prepare some artificial states, some artificial excited states. So we can prepare an excited state that look like the OH symmetric stretch, the OH asymmetric stretch, the bending of one specific mode or one other mode. And then when we do some cross-correlation function between our propagated wave packet and that specific type of state, we can see specifically on the spectrum where the features that are related to that specific mode are likely to appear. And that's what we can see here. For instance, we can see that the donor bond OH stretch is expected to appear around 3600. Similarly, that specific feature that was not appearing in the experimental spectrum from the group in China, which corresponds to the symmetric stretch of the acceptor, is also supposed to appear around 3650 wave number. So altogether, we can match in our spectrum those the features that we see in the spectrum with specific motion of the both water molecule, and they correspond quite well with the assignment that was made by the American group last year. But this gives us an explanation about the origin of the specific band, and this tells us also that the structure that they observed around 3550 was actually not the water dimer, and it's probably the water trimer as it was claimed in that specific work. But that doesn't tell us an explanation about the origin of this set of triple bands that we had in the initial experiment from China, and that you can also see in those other experiments. To understand this specific feature, you have to realize that those experiments were not done at 0 Kelvin. They were done at about 80 Kelvin. That suggests that when the system is prepared, it's not in the lowest state. It's actually in the slightly excited state. So what we did is that we also prepare a wave packet in that specific excited state, and we allow the propagation to go for some time. And when we observe the spectrum, is this specific type of feature we observe. So we observe an additional peaks that is appearing in this area. And when we combine those two parameters, of course, we have to take into account the spin and the autopara character of the water. But altogether, in the end, we are expected to see not only this main feature, the FD, but you also expect to see three other structures that you can probably see here. If we were running the calculation for a longer time, you will see it better resolved here. So to conclude this talk, I would like to say that we studied the quantum dynamics of the water in full dimensionality, fully quantum mechanically also, starting from the electronic structure to the dynamics. The spectrum agree well with the experimental data that were produced some years ago and settled some kind of debate and conspiracy and controversy that was arising on this problem. This work is not complete yet. Some of the simulation needs to run for a slightly longer time. We need to provide a more strict and robust description and theoretical analysis to validate some previous assignment that was done both experimentally and theoretically. But most than anything, this gives us some interest and some goal in studying bigger and bigger water cluster, because we have a very useful tool for this specific purpose, and we can really uncover some of the main features and main difficulties that has been arising in the study of those clusters. Finally, as I mentioned, this is a big collaboration involving people in various universities in the world, in France, in Germany, in China, and also this project is part of a bigger project that we are actually working on, that is on photocatalysis in collaboration with people at EPFL. I would like to thank the funding of EPFL UM6B and just to come and talk about science. Thank you.
Thank you very much. That was a great talk. So if people have questions, please use the hand raise function or drop them into the chat. But maybe I'll kick it off. So sort of a general question about what can you say about sort of the computer cost of generating the potential energy surfaces with the CCSD versus how expensive it is to run these dynamic simulations?
It's a tricky question because some people have worked on very efficient method to develop potential energy surface that doesn't require to spend a lot of time. I have the feeling that we spend a lot more time running the dynamics. For instance, those calculations can easily run for 1 month continuously using like 16 to 32 processors. So they are quite expensive, to be honest, the dynamics. The electronic structure, if you share your jobs, I guess in a few 1-2 weeks is done. But for this simulation, because you have to do some testing, it can take 6 months of calculation just to be able to have something that is sufficiently reliable. But yeah, I guess besides that, one of the main concerns is what we don't need is not really the electronic structure calculation, is the potential energy surface. So if you're able to generate the potential energy surface quickly, and you have a very smart way of doing it, I think it's always a better way. But for the dynamics, there's for now no way of going around this heavy calculation that takes a lot of time, and this post-analysis treatment that also takes some time.
Thanks. So David Vanderbilt asked a question in the chat. Is the dimer in an overall rotational ground state, or do you have to deal with the system being in a rotationally excited state?
Yeah, so when we prepare the system, in this case, it's rotationless, which is probably not the best way of doing it, but it seems that the main contribution are due to the vibration. Obviously, we were thinking about adding the rotation to the system, but it's just a few more degrees of freedom that we have to take into account. It's not impossible, but for now, we seem to have enough answer about the calculation without taking into account the rotation in our simulation.
And then we have a question as to why do you think that the discrepancy comes from the trimer?
Yeah, so when they made the measurement, there were two reasons. If I have to go back to that specific slide. Yeah, so there was some calculation that was done on the trimer before and some experiment, and they seem to show that there's a strong feature of the trimer that should occur around 35, 33. The other reason why they believe that is due to the trimer is because when you create those water clusters, I think the likeliness of contamination is very high. But for now, the claim was essentially is due to the trimer. That's also why we are thinking our next work will be to survey the case of the trimer. We already have a surface for that. We just need to prepare the calculation and check it in a more carefully fashion.
Great. And I guess this might be the last question before we move on, but are you certain that the initial, the CCSD perturbative triplet potential is accurate enough for these dynamic simulations?
Yeah, I strongly believe it is because, okay, first of all, the common understanding in the community is that it's called CCSDT gold standard. It's not always the case, obviously. But the main issue that you have with the CCSDT is usually when you try to look at the van der Waals connection for some specific system, where you may need to involve some excited states to describe correctly the long-range behavior of the system. But usually around the well, the results are usually quite accurate. And what we are trying to describe, even though it's a multi-well system, is essentially the dynamics around the well of the water dimer. So we do believe that the quality of the calculation are good, and many simulations that have been done looking at the intermolecular modes of the water dimer have been extremely accurate up to the 10 of a wave number. So there's a strong belief that this should be good enough in that specific energy range.
Okay, thank you very much.
Thank you.
Talk. All right. So our next talk is by Dr. Maria Chan. She works at Argonne National Laboratory, which is located near Chicago, Illinois. And today she will be telling us about using DFT calculations for machine learning.
Thanks, John. Is the correct screen showing?
Yes, it looks great.
Great, thank you. Yeah, thanks everyone for organizing this workshop. I apologize for not having been around the last couple of days.
Recording stopped.
I'm recovering.
Recording in progress.
I'm recovering from COVID, so things are a little bit.
Recording stopped.
Okay, do you want to start or stop the recording? Whoever is controlling it, John or someone else?
Recording in progress.
Okay, all right. I'll start talking. All right, thanks everyone for attending. Today I'd like to talk to you about how we use DFT and machine learning to understand and design defects in optoelectronic materials and conductors. This is quite a shift from the previous talk, which goes into great detail about electronic structure method, but Here, we are more focusing on large-scale electronic structure calculations or high throughput, rather, electronic structure calculations, and how we use machine learning to use that information on a data-driven approach. So I come from Argonne National Lab, as John said, and working in the Center for Nanoscale Materials. Center for Nanoscale Materials is one of 5 US Department of Energy user facilities for nanoscience. In particular, we have a theory and modeling group in the Center for Nanoscale Materials, and we have both theory and modeling expertise and computational capabilities. If anyone's interested in becoming a user, please contact me down here. So this general framework that I'll be focusing on today is on how we use density functional theory and machine learning to do materials design and understanding. We wrote a small overview or review article, really just a primer in Trends in Chemistry last year. It's a pretty new journal, so if anyone's interested in a copy of that, please send me an email and I'll send you one. So the general framework is that we have to first choose our chemical space, our structure, whether it's molecular or crystal type structure, and increasingly, want to tackle more complex structures, even things like polymer. And then we have to choose some recipe, right? Some ways that we're going to vary the chemistry or the structure of the system. And then once we figure out that these choices, we carry out high throughput calculations that can be any, many different levels of theory, but primarily because of the computational cost and sort of robustness that's the result of a few decades of work. Density functional theory is a favorite tool for this. There've also been a lot of development in the materials project group, and you'll hear more about it in the panel later, about tools that are used to automate calculations, DFT calculations. So we make use of that. And once we get the results of this, there's a lot of work in terms of visualizing the data, choosing the input that we're going to use to predict the output properties. These we call descriptors that are used to predict the properties of interest. Once we've decided on the descriptors, or we actually sometimes use statistical method to determine what are good descriptors, we train regression models that will give us the property given the descriptor. From that, we often plot a lot of these parity plots, which are machine learning prediction versus DFT calculations. Sometimes we call that the ground truth, although we all know here that DFT is a bit far away from the ground truth at times. But the goal in all of these is to get all the data points as close to this one-to-one diagonal line as possible, and you judge a machine learning model based on how close they are to this line. And then once you train some model, and we take a step back and think, okay, how reliable are our input data? Is there any way to improve on the reliability of that input data? Can we use more expensive, more accurate calculations? Sometimes the answer is yes, but in a very limited way. So we often use what's called multi-fidelity learning, which is when you use different levels of theory so that you have different levels of accuracy in your data. But you use your machine learning model to accommodate that, and that can be done in a number of different ways. But one very favorite way is what's called transfer learning, which is when you train a machine learning model on a lower fidelity data, and then have a smaller number of higher fidelity data, more accurate data, and that can be anything all the way to quantum chemistry, even quantum Monte Carlo type calculations. But because you have a foundational model that already tells you something close to the accurate results, additional training to get you the more accurate results can be done. Otherwise, if you only have a very small number of high fidelity data, it's very difficult to actually train a model that gives you good results. Once you have a good model, or sometimes, as is often the case, you have a number of good models, you can carry out combinatorial predictions, from all the possible space that you initially think of. You can carry out the screening on the properties that you're interested in. And I'll give you some example of how we do this. One area that we've done a lot of work on, and I should mention, and so listed on the slides, that a lot of this work was done by my former postdoc, Arun Menodi-Kenekatori, who's now assistant professor at Purdue University. So a topic of great interest for us is defects in semiconductors. Myself started being interested in this from a photovoltaic point of view. I've been working on photovoltaics for about 15 years now. The defects runs our show in photovoltaics. We need to know what type of defects are thermodynamically favorable, what type of levels they induce inside the band gap. And this carry over now to a lot of current interest in quantum information science, where people want to know defects and defect complexes and how they interact, and what kind of electronic properties they have in a semiconductor. So we carry out density functional theory calculations. A lot of this work was pioneered and developed in Chris van der Waals' group, including Chris Weisholtz, former group member of theirs, who did a lot of the groundwork, and we rely heavily on that. We start with density functional theory calculations of a big supercell with a defect atom. And then we use the energies that result from the calculation with a defect atom here, compare with the bulk, by which we mean no defects. And then we have to account for various chemical potentials of the atoms that were added or subtracted, as well as the electrons that were added or subtracted. We also have to account for a correction, because in a charge calculation, there is periodic interaction between the charge cell and the image charge in the periodic cells. And that causes an energy difference that shouldn't be there, and so that has to be corrected. From these calculations, we get something that looks like this. The formation energy of each type of defect is a function of the Fermi level. A p-type and an n-type semiconductor have different preferences for different defects. That's something that we intuitively know, but it's formalized in these types of plots. A positive charge defect is more likely in a p-type, so near the valence band maximum. A negative charge is more likely in an n-type, near the conduction band minimum. That's why the formation energy slopes up for positive defects, slopes down for negative defects. Every time the preference for a charge state changes, so +2 to +1, for example, at this Fermi level, the preference change from +2 to +1, that's a defect charge transition level or impurity level. And those are the levels that experiments can measure using DLTS, for example, or CL, cathodoluminescence, or deep transient defect spectroscopy. These are the defect levels that we would like to predict, as well as the overall energy of the defects. These calculations, of course, are expensive because they are large supercell calculations. So we would like to be able to skip over the DFT step once we've done enough calculations for training, skip over for the rest of them, and then use some sort of descriptors that describe the defects as well as this whole semiconductor in order to train machine learning model. We've done this on many different systems, and one sort of more general class of material that we've tackled are single-band semiconductors. So those are silicon and derived structures, including 2,6, 3,5s, and group 4 semiconductors. And we essentially put everything that is reasonable from the periodic table into the single-band semiconductor as impurities. So there's 77 elements that we picked from the periodic table. We don't really restrict based on cations or anions, just throw everything in. There's different kind of defect sites, substitutions on the A and B sites, the two types of semiconductors, as well as 3 different interstitial sites. And overall, if we had to calculate all of this, even just for stoichiometric semiconductors, we will be talking about 12,000 points. The idea is that if we can calculate a small number of this, we will be able to predict for everything, and not just for stoichiometric semiconductors. We will also like to tackle the off stoichiometry, which makes it infinite, right? Because let's say gallium arsenide, aluminum gallium arsenide, for example, that has infinite possibilities for aluminum and gallium stoichiometries. So we've done a subset of this, and we want to start by being conservative. So we do a large number of calculations here, for the 1,000 charge transition level and defect formation energy calculations. Here are just some scatter plots of the different results versus each other, not really meant to convey anything other than that, the data is there, and sometimes some of the properties trend with other properties. And remember, we need descriptors, which are inputs for the machine learning. So for a new defect and a new semiconductor, we want to specify a few things and then be able to predict the defect properties. We specify the host atom, the A and B sites in the semiconductor itself, and then purity M. We specify some coordination environment, what atoms surround this defect. We look at the elemental properties of the defect atoms. Those are things like electronegativity, ionic radius, and so it's very typical properties that you use. And then using all of that, we first take a quick look at the defect properties, which are the different columns here, and their correlation with all the input descriptors, which are shown very small here, but there's things like electronegativity, atomic number, and things like that. The reason we do this is to see initially what are strong predictors already. Of course, linear correlation is a very small, subset of possible different correlations, but it's a good way to just start and visualize. Of course, it's rare that you'll find something strong right in the beginning, and we don't. And so what was needed then is to have descriptors that are more general, because the formation energy should not necessarily depend on the electronegativity in a linear way. So we use Schur independent screening, sparsifying operator, or CISL technique, in which you combine the different descriptors in different functional forms. So you can have electronegativity squared divided by atomic number. I'm just making things up. But essentially we make up many thousands of possibilities of different combinations of descriptors. And then we use a sparsifying approach called lasso to reduce the number. So given all of these different possibilities, which ones still have strong correlation with the output or properties that we're interested in. So we pick the ones that we are that are strong enough to be predictive. And then once we've done that, we have our descriptors. And then we apply different types of machine learning approaches. Here are some examples. Shallow neural networks we use a lot of. A lot of times people look at deep neural networks for many types of problems, including computer vision. But in our case, because our training sets are really small in the machine learning world, numbering in the hundreds, we tend to use more shallow neural network with fewer parameters. Random forest regression is a very popular approach. Gaussian process regression is another. And in recent years, every machine learning approach has really flourished because of common platform for scikit-learn. So here's some example results. I said there'll be lots of parity plots. These are the formation energies as a function of the machine learning prediction versus the DFT calculations. What's interesting to note is that the blue is the training. So those are what we train the model with. The orange is yellow is the testing. So that's what we didn't put into the model. But importantly, we also add in off stoichiometry. I remember I mentioned that we start with stoichiometric material, just one cation, one anion, but we also want to know if it works on the mixed stoichiometry, two different anions in this case. And it turns out it does, slightly worse performance, but really very, very close. Here are some electronic levels, very similar story. In random forest prediction, you can also have uncertainties, so it gives you error bars, and that's nice. The uncertainties are a little large here, and that's quite often reflective of this relatively small number of training data. So that was a cadmium chalcogenides, just a specific example. If we throw in all the chemistries into the same model, so this is the challenge. A lot of times machine learning models are very specific to one chemical system, but we actually are tackling all the chemical systems. Transition levels are more accurate in the occupied levels. The negatives are the occupied levels, which is not surprising given what we know about DFT. The formation energies have a somewhat higher uncertainty or error, but that's also part of the fact that the formation energy has a much bigger range than the transition levels. With neural network Gaussian process, we actually get somewhat similar results. With all of this, we have developed an online tool for predicting the results from machine learning models. That's listed in the paper, and I can send you a link if you're interested. People can input the type of impurity and the parent semiconductor, and then get a result of all the predictions from the different machine learning model. All the data from this paper is also made available. Everything's listed in the paper, so if anyone wants to play with the data and train a new model, they are certainly welcome to. So that approach, of course, is also generalizable to other types of systems. We also work on impurities in perovskite mixed halides. In this case, it's the same thing. You have methammonium lead, but different types of halides. We train only on stoichiometric halides, so iodide, bromide, and chloride. But then we also, or actually half bromide chloride in some cases, but we also tested on off stoichiometry, on mixed stoichiometry. So this result is in this paper here. Again, we look at correlations between the individual properties predicted and the input descriptors. Here we use something that's somewhat unusual for descriptor. In usual calculations, in usual machine learning projects, you would have descriptors that are evaluated from the structure alone, or even just with the composition alone. But we chose to do a small calculations in which here MAMX3 means that instead of lead, we input the impurity into the lead position and do a single unit cell DFT calculation. That turns out to be hugely informative. Of course, it's much more expensive, compared to evaluating the electronegativity or the atomic number of an element, but it's much cheaper compared to doing an actual supercell calculation. So you're talking about 12 atoms instead of a 100 or 200 atoms calculations to get the proper defects. But these values, you see the very dark black, that means they have very strong correlation with some of the defect properties, and we find that to be a useful way. So with those descriptors, we again use different types of machine learning models. The results are actually quite a bit better. I mean, in a sense, you expect it because the chemistry is less varied in this case. We just have the methammonium lead halides, very similar chemistry, whereas previously we're trying to do carbon and silicon and zinc oxide all the way to very low gap semiconductor like germanium and high and low electronegativity difference in different thin gland semiconductors. Here is much more tight, chemically, and so we have essentially a bit better predictions from that. And here's a blow up of some of the results, and the transition levels are especially well predicted, at least the one close to the 0. We test the approach on out of sample results here. Those are not used in training, and it's important to do this because we want to know how generalizable our models are. So, previously all of this work has been on defects, just putting impurity atom into the semiconductor. But then, we also asked this question, and this is not new. A lot of people have done similar work in many different materials. How do we actually design the whole perovskite? Can we change A and B on top of changing C? And from that, we need a lot of different properties to determine if it's good for photovoltaics or other optoelectronic applications. We need to know if it's stable. We need to know if the band gap is good. We need to know if the absorption spectrum matches well with the solar spectrum. We need to know if it's defect tolerant, and so on. So we actually went and calculated a bunch of this for 5 different A sites, 6 different B sites, and all the halides. If you alloy the B sites, which is very commonly done, you can have, even just for discrete alloying 1/8, 18,000 compounds. And then here, but of course, the alloying doesn't have to be in 1/8, and that means there's, infinitely many possibilities, but let's just take 18,000 as a number of possible combinations for this supercell size that we choose. We do just 200 calculations. In both PBE and HSE, and calculate all sorts of properties in the table I showed earlier, decomposition, band gap, and so on. The neural network models shows really, really good predictions. These are shallow neural networks again, very, very accurate predictions in terms of decomposition energy, decomposition to the binary compounds, band gaps, both in PBE and HSE, and things like refractive index and figure merit, which is related to the absorption spectrum and is matched with the solar spectrum. Again, we test on out of sample. So now we mix the A site or the X site, mixed halides or mixed A site cation, or new B site elements that were not included in the original training, as well as different size supercell. The supercell size actually doesn't matter at all. I mean, you don't see much difference, but even new chemistries can be tolerated. It's not as good, but it can be tolerated, and you get some useful predictions from the model. Stuck here. And then, once we have that, we have done a lot of screening from those 18,000. We eliminate different things based on different criteria. Once you look at stability, potassium is eliminated. That's the reason you don't see potassium perovskite materials being studied. They just not stable. With band gap, we then come down to lead, tin, and germanium, and not calcium, which sort of is reasonable. Defect tolerance actually was instructive because it eliminated all the chlorides. Only a few cesium and rubidium are left. So cesium, pure cesium perovskites are known to be not as good in terms of performance, and also pure chlorides are not good in terms of performance, and defect tolerance could be why. So we have results of a list of possibilities that are worth further investigation. This work just came out last month from in Energy Environmental Science. We also have, I didn't call out all the papers, but we have a paper on patterns on the SingFlan work, which includes all the information about the data and the codes and the web interface and so on. So with that, I like to just conclude here about our work on DFT machine learning for semiconductor and defect design. We do some small number of DFT calculations relative to the chemical space available. And then for single-lens semiconductor, we train a single model out of all the chemistries for the defect properties. For perovskites, we look at impurities and also different types of properties like band gap and absorption. And then in both cases, we test the models on out of sample cases, that things that the model has not ever seen, or it's different in some way from the training and test data. We find that regression models doesn't make a huge difference. There's some slight improvements in some cases, and Gaussian process is more likely to overfit, for example. And then I haven't shown a lot of details, but there's another paper that we've shown how if you have more expensive DFT calculations, you can approximate it by cheaper DFT calculations plus machine learning. So how much time do I have? I have a few overview slides on other efforts in our group, but it seems like we are running out of time.
If you want to flip to it, and then we can start taking questions.
Yeah, sure. I see that there's some chat questions. I'm going to skip over this one. So, and some other work that we're doing in our group has to do with inversion or characterization data, finding out structures from spectroscopy or microscopy data in particular. So I'm skipping this. In some cases, we predict from spectroscopy the coordination number of atoms. In some cases, we reconstruct three-dimensional atomic structure from electron microscopy images, and also scanning tunneling microscopy images. We have a fully interactive iterative search approach that uses both experimental and theoretical information to determine structures. It's an example for electron microscopy. The reason we want to do this is so that we can have more accurate, realistic structural models, because a lot of times we can make a lot of models as theorists, but they can be a bit idealistic and not necessarily realistic or found in the actual samples. And finally, and this will be my last slide, we are using computer vision and natural language processing to extract information from published papers. This is really useful because there's so much information that's locked away from past literature. This GitHub hosts some of our codes and data. And I would like to acknowledge funding from DOE. And I'm just going to leave this here, and thank you for your attention.
Okay, thank you very much. So as people have questions, just raise your hand, chime in, or drop them in the chat. And maybe we'll start with, so how often are you able to make machine learning descriptors that are sort of human interpretable, right? That they could tell you something about the chemical motifs or something like that.
Yeah, so yeah, sometimes the digital approach is really nice in that sense, because you start with descriptors that are already physical, like electronegativity, or the valence band maximum value in a small unit cell calculation, and then it makes combinations of them. So you'll be getting functions like e to the x over y, or physical functions like that, and then you can see how these different descriptors actually go into the function and predict the property. So it's almost like an equation learner in that sense. So that's quite nice. I do think that when you predict material properties, it does give you more leeway to get meaningful descriptors compared to things like spectroscopy or microscopy.
All right, thanks. And so a question from the chat as well. So we know DFT often gives incorrect band gaps, predicts insulating materials to be metallic. How do you deal with this in your data set? Are you using a GW correction or?
So this is an interesting point. There's a work by Peter Schultz at Sandia. It's a while ago now. That has, basically he did these defect calculations for different semiconductors, and he find that although the DFT Kongshan band gap is wrong, the defect transition levels, which are energy differences, actually span the physical gap. And this is what we found as well for a lot of these materials. And what is happening is that, we are doing essentially delta SDF type approaches because we're calculating energy differences for different number of electrons. And we're using the DFT total energy rather than the Kunshan band gap directly. So because of that, the defect values are actually quite reliable. I didn't show it here, but in our paper, I can send you that PBE level defect transition levels actually agree reasonably well with the experiment. We checked HSE results, and they are not actually much better. I mean, actually, in some cases, they are worse. So because we are using total energy differences, the band gap problem actually is much less than you think in these defect calculations.
Thanks. And I actually want to jump back for a second to the data availability you mentioned. So you have both the machine learning and the raw DFT results are available.
Yes, machine learning predictions for all chemistries, as well as the initial DFT calculations. Not raw per se as in all the output files, but the calculated, the properties that we calculated, the formation energy, the delta H's and the epsilons, the defect transition levels.
Yeah, so that means that if someone was interested in exploring this and exploring machine learning, they could simply have access to your already done DFT database and jump right in.
Yeah, and we'd be happy to chat with them or work together, or send you where it is. It's listed in the papers, but yeah, I can point you to it. I'm also hiring postdocs and interns. If anyone's interested or has a student or colleague, I'll be very happy to talk to them. Thank you so much.
All right, thank you. So maybe another round of virtual applause for both Maria and Steve for this morning's talks. And I'm gonna pass it off to Amy, I guess.
I'm going to pass it off to Sinead.
Yeah, we're batting each other around. Good morning, everyone. Hi. Okay, so we have a bit more of an open format session now. So this is going to be some opportunities that are available to those of us on the call and in the network. And we want it to be interactive, so please interrupt. The speakers aren't really speakers, we're just giving information. I'm going to give you an overview of who's going to be talking about what right now. So we have Professor André Schleife first, and he's going to tell you about some opportunities with the Institute of Physics's Electronic Structure Journal. Then Dr. Matt Horton will tell us some opportunities with the Materials Project, and almost perfectly timed right after Maria's talk, where we can think about data availability and where we can maybe get some good quality data for doing these sorts of machine learning approaches. You'll hear from me again, and then we will have Jingyi, who's a PhD candidate at Columbia, talk about how we can all stay connected and the different types of resources we've set up through USAfri. And then finally, Amy will discuss some videos and interviews that she's been preparing and will happen over the next few weeks. Okay, so and as I said, please do interrupt us. This is supposed to be more of an interactive session where we can exchange information, and please share with us as well other opportunities or resources that you think your colleagues here should be aware of. So let's start off first. I'll introduce Professor André Schleife, who's going to talk to us about this IOP journal on electronic structure. So André, I'll let you take it away.
Great, let me just share my screen real quick. I think it should be this one. Can you see this slide? I didn't bring many slides, but can you see the one that's on right now? Perfect. Okay. All right. So my name is André Schleife. I'm at the University of Illinois, and today I will not tell you any science, but how to publish some science. Okay. Sorry, my Zoom just switched. And in particular, both Sinéad and myself were on the editorial board of this journal by IOP. The title of the journal, or the name of the journal, is Electronic Structure. It started in 2019. And the brief gist of this is that the journal Electronic Structure, so the acronym EST here.
André, your screen stopped sharing.
Oh, sorry. I don't know what happened. Hold on a second here. Let me try this again. Yeah, see, my Zoom snapped, I think. All right, here we go again. Is that better?
You're back again.
Awesome. All right, let me go back to laser pointer here. Anyway, so what I was about to say is that this journal was launched in 2019, and the idea is that it publishes multidisciplinary research. So that in particular means theory and experiment. So precisely along the lines of what we see in this workshop, there were a lot of excellent talks, largely focused on theory, but connections were made to experiments. And the joint factor or the common factor here is electronic structure. So in particular, this includes material science, physics, chemistry, and biology. So I think a lot of the topics that were presented in this workshop actually align very well with this journal. And here I just want to mention that and bring some awareness to this journal to you guys. So the editors-in-chief are Berthe Zhuang at Lawrence Berkeley National Lab and Risto Niemann at Aalto University. And you have some contact information here. Emphasis is that the journal is multidisciplinary and interdisciplinary. The research is high impact, just as the talks are in this workshop. And there's rigorous peer review. So the journal is new, which is why it says here that it's just accepted for inclusion in these citation databases and things like that, but that's on the way. And what I want to show you is two more things, and then you guys can ask me any question. The first one is the editorial board. So these are the people who are on the executive editorial board here. Many names you will recognize, and in particular, you will see the interdisciplinarity here, right? So in this group, we have people from the ICTP, and we have people from the African Light Source. So all of that research, I think, aligns very well with the journal. And the last thing before you guys can hit me with any questions is, I want to mention two things. The journal publishes special issues, okay? And in particular, we want to, so Sinéad and Richard and myself and others who organize this, Renata, want to publish a special issue on this second USAfri workshop. And so there will be an editorial piece written by the guest editors. The specific deadlines are still finalized, but that's nothing for you to worry about, because you can submit your papers anytime and they will be published incrementally, meaning we're not waiting for all the papers to be there and then the journal, the issue comes out. You can submit, and as papers are accepted and make it through peer review, they will appear on the website and they will list it in context of this special issue. There's no fee to publish. That's a plus. And if you want to publish open access, there is the possibility of fee waivers. So that depends a bit on the details on where you're submitting from and things like that. But as I said earlier, contributions are welcome from the ICTP and from the African Light Source. So I put in bold here what I think you guys should be doing after I'm talking. So for the first one is submit your work to this special issue. If you're presented, write up a brief manuscript and submit it to the special issue. We would be super happy to see that. The second thing I want to briefly mention is there is always an annual issue on emerging leaders. And again, many of the presentations that were here in this workshop align very well with those requirements. The call for that is not out yet. It will come out very soon. There was a previous one in 2020. And the idea is that this provides visibility to the people who publish there, and the selection process is competitive. Action item for you guys, reach out to the editorial board for nominating your work. So the way you'll be included in the special issue is there will be nominations through the editorial board, which again, the names are here and also on the website. So if you think your research aligns well with this and you would like to contribute to this special issue on emerging leaders in the field of electronic structure, contact any of the editorial board members, ideally one who's kind of aligned with your work, and then I'm sure they're more than happy to nominate you to contribute to this special issue on emerging leaders. Again, the call is not out yet, but you have all these infos here. It will appear on the website and all these kind of things. Okay, so I think at this point I'll stop. If you have any questions, please feel free to ask. But again, these two bold items are the take-home points. All right, I'll leave my screen shared here. The chat is full. I don't know what's happening here. All right.
So Michelle has a question.
Go for it, Michelle.
Yeah, thanks for this information. Just a question. Lots of the funding agency now requires to have article being open access after a year or so. So what's the policy here? If we choose not to have it at the start, like pay for to be open access, but take the free access, but when does it become available? Freely available?
That is a great question. I don't think it automatically becomes, I don't think it automatically becomes free. It's a hybrid journal, and I think you can decide if you publish for free or if you publish open access.
Can you tell us maybe then what's the are we allowed to publish the articles on our website or some archives which will satisfy funding agencies?
That's a great question. So I think I have to double check the precise policy. I don't know this by heart, but I think what you can do is typically you can submit the non-edited and non-peer-reviewed version of your manuscript. You can self-archive that on your institutional repositories and things like that. I'm not 100% sure about the policy of the final edited and peer-reviewed version of the article. I'd have to double check that on the website. But in particular, so there is a list of countries that is defined by the World Bank, and for them fee waivers apply. And those can publish either at a 50% reduction of the fee or even 100% reduction of the fee. So that list, if you're interested, I'm happy to share that list in the chat. That's also on the IOP website. But if you're submitting from one of those countries, you can publish for free and open access from the get-go.
Yeah, I don't think Canada is part of that list for sure.
No, Canada probably not. That's true.
I think there's already a reciprocal agreement with Canada, Michelle, that covers the open access.
Oh.
Yeah.
But sorry, what is collaborative work? Like there's some scientists from Africa and others from Western countries. Which one takes the lead?
Sorry, can you say that question one more time? I'm not sure if
I say, what if it's a collaborative work? So there are some scientists from Africa and other scientists from Europe or the US. How does it work?
I'm not sure how they would handle that. I guess maybe the corresponding author's affiliation counts or something like that. But that's a great question. I would have to ask I would have to ask Katie. So Katie is the publisher, and I can ask her that question easily. I think typically the corresponding author would be probably the what determines that. But don't hold me legally to that. All right, I see. Okay, there's one more hand up. I don't know. Prosper, do you have actually a question, or am I misreading my Zoom?
Yes, I have a question, if I may ask.
Go for it.
Yeah, do you hear me?
Yeah.
Yeah, good. So I'm happy to see about this journal, and also to see that you took into consideration the African rights source. I say it because I'm part of it, and I know how things are going. And my question is for the special issues. For example, in the African rights source, often you have every year conferences, and some people want to publish, for example, proceedings of the conference of the African rights source conferences. So is it a possibility to consider some proceedings which are in line, of course, with electronic structure related experiments or theory? Is that something to consider for your journal, or proceedings not something you to consider for your journal?
Well, so I think the journal does not typically just publish a proceedings series, but you can submit that, number one, as a regular contribution to the journal, and number two, you could, if it aligns still. See, I think this first special issue that you see here on the topics, this is what I inserted here, the topics aligned with the second workshop. I think the journal would not be against you submitting to that special issue if the work that you're submitting aligns with the topics discussed in this workshop. So I would say these two options you have. I don't think they do like a full series of proceedings on a specific conference. I think we could pitch the idea to Katie, for instance, if you know at that conference you have, I don't know, 15 people who would like to submit something, maybe there is the option of making a special issue on the topic of that conference if it does not align well enough with this workshop that we're at right now. But that's something we could discuss with Katie. But I think there's no like standard proceeding series that the journal does right now.
Okay. And also, if I understand well, you take both for theory paper and experimental paper related to electronic structure.
Absolutely. And in fact, I think one of the things the journal wants to strengthen is the experimental side, because for, I don't actually know for what reason, but for maybe historic reasons, electronic structure in the community is oftentimes perceived as computational work and simulation work. And so I think one of the things the editorial board discussed in their last meeting is that we would like to solicit more experimental contributions.
Yeah, because I'm experimentalist and we do, for example, our pace, this will be an interesting, of course, one have to take into consideration of details, but it is good news, yeah. Thank you.
Absolutely. No, this fits very well. Like I said, it's not just theory, and it's absolutely not just condensed matter. Like, for instance, if people work in, we saw water-related research and things like that. So as long as electronic structure is the topic of the research, it fits with the journal.
Well, thank you very much. All clear. Thank you.
Thanks, Prosper.
Okay, if there aren't any more questions, then I think we'll hand over to Matt Horton next from the Materials Project. But thank you, André.
Thank you, guys.
Hello, everybody. All right. I do have some slides today. Can everybody see this okay? We're good. Excellent. All right, so I'm here today as a representative of the Materials Project, which is based at Lawrence Berkeley National Lab. So I just wanted to go over sort of a few different ways that people interact with the Materials Project and sort of talk about what our collaboration sort of structure looks like. So for anybody who isn't familiar with the Materials Project, this was something that started out with the Materials Genome Initiative back in 2011 to give open web-based access to pre-computed information on materials and to make analysis tools to help generate new and novel materials. So out of this came the Materials Project, which is now this big database and website of inorganic crystal structures. So in terms of opportunities and collaboration, I'm going to go through these different points. So there's using the Materials Project data that we already make available, sharing your own data, different learning resources that we have, how we develop our code and how we collaborate on sort of tool development, and also direct collaboration opportunities. So for anybody who hasn't seen the Materials Project database before, we now offer quite a number of pre-computed properties on a lot of crystal structures. I think about 150,000 crystal structures. We have sort of geometry optimized sort of ground states. We have electronic structures, so band structures, DOS, phonon dispersion for about 10,000 or so materials, a lot of elastic dielectric and piezoelectric tensors, X-ray absorption spectra on a per site basis. So we've just added LH spectra for that as well. And we've also just started to provide charge densities for a lot of these materials too. I just want to emphasize that this, yes?
Are you still supposed to be on your first slide?
I am not.
Okay.
Thank you for saying so. Which slide was the last slide that you saw? This one?
It was still on your title slide.
Okay. Interesting. Can you see a different slide now?
Yeah, now I see Materials Project data, and you have your year versus database entries.
I'm a little bit confused at the moment. Okay, what do you see now?
The same slide.
Okay, I apologize for this.
You can just show this view and zoom
I will just show this view instead.
Yeah.
You can spend every single day of your life on Zoom and still stuff happens. Okay. All right. Well, this was the, Materials Project introduction. This was the opportunities and collaboration that I wanted to go over in this talk. This was the slide on what data we have available. And I was just about to say that, the emphasis I want to make about the Materials Project data, we do put in a lot of effort to make sure this data is good, and we're really proud of it. But at the end of the day, it's not a substitute for detailed studies. We really give this data as hopefully it's useful to people as a starting point for future work. Okay. So to use the materials project data, all you need to do is log in. Then you can start to explore it on our website. This is usually how people sort of start to get a feel for what data is available and sort of the overall scope of the database. After that, we now provide one-click interactive coding environments. So we will give, if you're interested in getting a little bit of the data and start to use it in data pipelines, we will give a little snippet of code that you can copy and paste, and a coding environment that can run entirely in your web browser to start playing around with some of the tools that we offer. So the other thing that we have just started doing is using the materials project as a platform to share data. So obviously, Materials Project is a fairly high traffic website at this point, and high traffic websites are a platform because they often appear in search results when people are searching for materials. So we really want to try and use this platform as a way to improve the visibility of research of others as well. And so to do this, we launched a project called MP Contribs, which is where researchers can upload data themselves to Materials Project, and then it gets shared on the Materials Project. So people who do this, you still own all your data yourself, but this upload can be linked to any relevant publications so that people can find the papers associated with this data very easily. And it also has an API, so anybody doing their own sort of big data studies and machine learning studies can easily download your data as well, if that's what you want it to be. So MP Contribs is now available for general use, and we have a few dozen different sort of third parties who've uploaded their own data to be hosted at MP Contribs, and is now discoverable online too. So for code development, in the Materials Project, all of the tools that actually generate all of this data, our website, and support our high throughput infrastructure, all of this is developed in an open source manner. So that means that it's all freely available to download. The history of our code is all available online. And importantly, any discussions about new features also happens in the public. So, you know, it's very common for if there's a community need for a new feature, or if somebody finds Materials Project tools useful for their own research, that there'll be a discussion online about improving a specific feature. We have a lot of people who've now contributed code to a lot of our projects. And if anybody here is interested in being a part of that, you're really, really more than welcome to get involved and start a discussion, and I'm happy to talk about this in more detail too with anybody who's interested. So we have quite a number of codes now for different applications. So this includes PyMatchN, which does a lot of data analysis of crystal structures, can generate phase diagrams, but we also have codes that can help doing error correction in calculations when things go wrong. We have codes for doing workflow management that can run on a variety of different high performance computing systems, and can reduce the amount of work necessary to run a lot of these calculations. Okay. We also have a lot of resources for learning. So we have an annual workshop, and videos and notebooks from this workshop from previous years are all available online on YouTube. And very happily, we had a few participants from this initiative last year. So we're still not sure if this workshop will happen this year or not, but if it does, I would love to have more participants from USAfrI there as well. We also recently launched a new monthly seminar series as well, which is to share different research stories that are happening in the community. And these are also available on YouTube. And finally, for resources and learning, we have this big online forum, which is at the domain matsci.org. where we host discussions, not just for the materials project, but for a number of other codes and collaborations. So like LAMPS, like ASC, Nomad, PyMatGen, and the rest of it. So we really wanted this to be to act as kind of like a public kind of town square for discussions, and not to have any sort of particular preference for any one project, and as a place for people to both to ask and answer questions, for their area of expertise. And everybody's very welcome and encouraged to join the conversation here too. And finally, I just want to say that there's always an opportunity for direct collaboration with the materials project team when it aligns with our goals. This does happen a lot, and I'm very, very happy when it does. So if you do have an idea for a research collaboration, please get in touch. On this slide, I just highlighted 3 kind of random papers that I've been involved with over the last 2 years, but I highlight them just to say they were fully remote collaborations, and actually 2 of them did not start with any pre-existing professional relationships. So they were just connections that came about because I was chatting to somebody on one of these forums or on GitHub for the code development, and we had discussions, and it led to peer-reviewed publications. So I just hold these up as an example that remote collaborations can work. They can work well, and I'm always happy to facilitate them where possible. So this is just sort of the quick overview of what we're doing at LBL as part of the materials project. But if any of this is of interest to anybody here, please get in touch, and I'm happy to talk about it more. And that's it. So thanks, everybody.
Great, thank you so much, Matt. Does anyone have questions for Matt now? Oh, there's one in the chat. Yeah, go ahead.
I can answer that. So can we download Quantum Espresso input files? The answer to that is not directly, but it's fairly easy to do. So with Materials Project, you'll download the crystal structure, and then with PyMatGen, you can convert it to a Quantum Espresso input file in like one line of code. So it can be very quick to get from the crystal structure to the input files. We don't use Quantum Espresso a lot ourselves, but we do have some support for it. We have a lot of support for Abinit as well coming up.
Any other questions for Matt for now? Steve.
Yeah, sorry. I wanted to know, because you host a lot of data, how do you, how can you ensure the integrity of those data? How do you check the quality of the result? I mean, that specific aspect is always a bit confusing for me.
Yeah, it's a very fair question. So we have the Materials Project core data, which is the data that we generate ourselves, and so we take responsibility for that data and making sure that it's calculated in a consistent way and that it is benchmarked against experiment wherever possible. So for each of our different data sources, there's usually a publication which goes over the experimental benchmarking that we've done. So for example, the elastic tensors, you can look up how our calculated bulk moduli compared against the experimental bulk moduli. This becomes very important because some of the methods we use are not that good, in the sense that in order to do it at a large scale, we cannot use the latest and greatest methods, right? So we're not calculating band gaps with GW, we're calculating them with PBE, and there's that big underestimation that is not always obvious for people coming to the materials project who are not familiar with the methods that we're using. So it's always important to sort of look at those publications. But that's for the MP core data, which we take responsibility for ourselves. For the contributed data, for people who upload their own data, that just gets linked to the relevant material, but it's ultimately the responsibility of the person sharing it to make sure that data is good, and it's their name on it and it links to their publications, and then it's just down to the judgment of whoever's using the data for how much they want to trust that or for how it was generated.
Okay, thank you.
Thank you. I think I saw there was a question from Fatima as well.
Yeah, Fatima, did you have a question?
Fatima,
Yes, I
sorry.
wanted to ask something similar. Just, yeah, I was searching in the material project website a couple of days, and I was trying to find like some reference to the data that are present there, but I couldn't. For example, if some related experimental data, or I don't know, even like because they are calculated and reference for the calculated results, and I couldn't find them there. Difference, yeah.
Okay, so just to make sure I understand, so you were looking for some information on the materials project that you couldn't find.
Reference to the
what
data
data
that
specifically?
exist there, yeah. I mean reference, yeah.
Reference data, like what? Like what specifically? What kind of data?
Okay, so I was looking for helium, let us say, in the hexagonal closed bucket structure, and I was looking for like some reference for the calculated structure, or some, let us say, I don't know, some experimental data reference to the structure, something like this.
I see.
Yeah.
Yeah. Yeah, there's not experimental data. There's not an experimental reference available for all of the entries in the materials project, because we calculate data for far more materials than have actually been studied experimentally. We do have references when we get a geometry, like a crystal geometry, from an experimental source like the ICSD. We do have a reference to that. I will say, if there was specific data that you were looking for and you couldn't find it, just send me an email or ask on the forum, and I'd be very happy to track that down. Because if the reference is available and you weren't able to find it, that's ultimately a problem on us for having a confusing website or something. So I'd be very happy to know about it and try and fix it. And yeah.
Okay.
Does that kind of answer your question?
Yeah, thank you.
And then I think we'll finish up with the last question, which was, oh, you got it. I got it in the chat.
Yeah,
okay,
I got
great.
it.
Awesome. Thanks.
Right.
Okay, thank you so much, Matt.
Thanks very much, everybody.
Okay, let me share screen. It's my turn next. Here we go. And you can tell me if my slides aren't moving on, so that I'm not talking to myself. Okay. So I'm going to tell you about some opportunities that have deadlines that are coming up close, and then just a bit of a broader oversight of how we're going to connect together, and some opportunities and resources that are available for the community here today. And so the first one, which you're mostly aware of, I think, is that next week at Columbia, the electronic structure workshop is taking place. So it starts, the scientific program is Wednesday, Thursday, and Friday. And, it is recent developments in electronic structure theory. So all of the workshop strongly aligns with what we've been trying to do at this workshop as well. I will, though, for those of you who aren't aware of this yet, the online registration is still open for virtual participation, which is free. So you can attend and see all of these talks. Here's a snapshot of some of the invited talks. You can attend and see these all for free. So the discount code is free to waive the charges to virtually participate. So this will all be online if you go the virtual route. And I believe, but Renata can correct me if I'm wrong, that the videos will also be available after, so you don't need to watch them live as well. So all of these resources, by the way, all these slides will be available on the USAfrI website right after this. So you don't need to try and take down the URL or anything. I'll have these all up available so you can get the connections and the links. Okay, so that's the first one. The next is ASESMA 2023. So ASESMA is happening again next year, as some of you probably know, and it's planned for the ICTP in Rwanda. Did you want to say anything about this, Omo? Or I guess we're still planning, so I don't think we know dates yet, but it'll most likely be next summer. Yeah. So keep an eye out for the announcement for assessment, which usually happens, if it's next summer, it'll usually happen around January time, December, January. So that's assessment next year. And then related to assessment is this assessment launch, assessment.net launch, which we did for the first time, I think 2 years ago. But something happened in the last few years that allowed us not to successfully do this. But what assessment is it's related to assessment.net is related to assessment, but it provides travel funding for collaborations between African scientists and a collaborating country. So it's very similar to what we're trying to achieve with USAfri, which is basically you can spend a period of time in a collaborators group, and assessment will cover the flight tickets, the travel, accommodation in the host country, and the living allowance in the host country. But it's within Africa. So basically, if, for example, Prosper wants to collaborate with someone doing, advanced electronic structure theory in Ethiopia, then that would be the sort of thing that this will cover. And it's open to lecturers at institutions in African countries who want to carry out research in atomistic or molecular modeling. And the deadline for that one is soon. So that's June 15th. Okay. The next one is related to University of Columbia. So the Columbia Global Centers have several different sites throughout the world, but there is one in Nairobi. And they are very open to collaboration with African scientists for things like hosting workshops and facilitating connections and collaborations. And there is a grant competition every year to get grants to run these sorts of events. That's run through the Columbia President's Fund. So the website has more information about these sorts of deadlines and what opportunities are available, but the Nairobi hub would be really the central one that's relevant to us here. And I know a lot of you already through assessment, so seeing you all on Zoom is great, but actually I've met this giraffe before, and I don't know if you've seen this picture. So I actually met this giraffe as well at assessment one year in Kenya when I visited the Nairobi sanctuary right outside of Nairobi. Okay, next is this wonderful opportunity, and you can see Asasna Haile is one of the key organizers for this, which is a National Academy Symposium, and this is the Africa Frontier Symposium on Science, Engineering and Medicine. And it is aimed at emerging leaders in the field of science, engineering and medicine. And it's going to take place in Nairobi in October. So this is aimed, as I said, for emerging leaders in these fields. All of the eligibility requirements are on their website, but the one thing is that it is aimed at kind of more assistant associate level professor. So what that means is that you got your highest degree, so your PhD, less than 15 years ago. And there's some other eligibility requirements, be employed in either the US or an African member union, and obviously work in the fields covered by the workshop. And one thing I will say is that there are 5 symposium or 5 different topical areas at the symposium, and 2 are very much related to what we're doing here. So there's one on AI machine learning, and there's another on material science. So actually, I think there's a lot of opportunities for people on this call to participate in the National Academy Symposium. And the deadline for that is June 20th. Okay. And then I think this is the final one. So then also do keep an eye on opportunities through the ICTP East Africa and the ICTP in Trieste. One thing is, of course, the ICTP East Africa's master's program is going, yes, the deadline is tomorrow, I think, right? Or in a day or two. So if you are planning on applying, you better get your application in quickly. So this is the first thing. And the second is through the ICTP in Trieste, they have the scientific calendar where they'll list, the programs, events, workshops. Keep an eye on that as well. There might be workshops you want to go to. They've actually put all of their seminars online now, so you can access a lot of the seminars of the ICTP virtually now. And then finally, a reminder to sign up for the PsyK mailing list, which is the mailing list that has a lot of announcements based on electronic structure, whether that be job announcements, workshops, or different opportunities, PhD positions, etc. Okay, that's all I have. Are there any questions on any of that? Okay, I'm going to hand over to Jingyi now, who's going to tell us about some ways of connecting after the workshop.
Great. Can you see my PowerPoint? Or no?
It's still loading, I think. It's
okay. Just give me one more second. Let me just do this. How about this now?
Yes.
Okay, great. So hi everyone. I'm Jingyi, a PhD candidate from Columbia University. And before I get started, I would like to acknowledge my group. We are a Wavepacket group working with Professor Renata Wavepacket, and I'm putting the Zoom helpers here. Thanks Chi, Hongjing, and Chenxing for being around, for being our Zoom helpers. And my topic is social media channels for USAfri. We have various social media information services, including our website, our YouTube channel, our Slack channel, and our Twitter. I will use these icons to represent them in the following slide. And they serve for the same major purpose: help you reach USAfri initiative. And first of all, this very important website, USAfricainitiative.org, contains everything about us, like introduction and news here in the homepage. And you can see in the banner, there is programs for the previous workshops, and also about us, events, and peer programs. So we would like you to check this from time to time to get up to date, get updated. And you might already be very familiar with this page, the scientific program of our current workshop. Amy has put a lot of details and all available resources like slides, videos on it. So you can just feel free to check in and click any of those to see it. The second social media channel I would like to introduce is our YouTube channel with this title, USAfrica Initiative. We created and highlighted 2 video lists to the 2 workshops we have already conducted. And the recordings are available and easily reached by searching USAfri in the YouTube search box. And an example of our recording would be our group photo taking on the first day of our workshop, just seeing everyone's smiling face here. And the third social media channel is Slack. Slack has many functions, many functions, but for people like me who do not know very well, it is an advanced chatting app for me. Capable with group chat and private chat, with perfect memories of storing the chatting history, images, PDFs, links, and everything. In our usafri.slack.com channel, we could have Q&As in the workshops. We have event announcements, and we have announcements for seminars, for the examples like here, hosted by USAfri. And we also broadcast talks of interest. So I'm going through it very fast. If you are interested in any of these ones in detail, just join us, join our Slack. And also these informations are also available in our main website. The last social media, which is opened very recently, is our Twitter at USAfri_ES. During the days of the workshop, we broadcast daily schedules with flyers like showing here. We have flyers for everyone, every speakers. And it serves as a perfect timeline from our very beginning, the group photo of our last workshop, like seen here. And then to the time before the workshop, when Annie arrived at André's research group and took a group photo in UT Dallas. And we would accept to do this for every people arriving here next week. And we would like you to meet with your host and take a picture. Then to the time we posted our workshop schedule flyer, and we have more to continue. And here we would like to encourage people who are using Twitter to join us by either mention us at USAfri_ES, as we can see Prosper here. Thank you so much, Prosper, for joining us our timeline. And or we can just tweet with hashtag USAfri. By searching this tag, we can find a timeline contributed by all USAfri people. Like here, we can see USAfri posting a lot of informations and a palm posting the links, and we can see Google Letter here. It's so nice to have you. And a simple start would be like this. Type in USAfri, hashtag, and just join us. So maybe you can just write down your favorite parts and what you found most useful for the workshop. If you do not use Twitter, which is totally fine, because we are not here to promote Twitter app, but the USAfri, we are promoting ourselves. And if you're still interested in joining our timeline, please send us an email with your favorite USAfri photo to our email box. And the email box can be found maybe in the Zoom chat later. And lastly, here is a simple overview of all our platforms and channels. And so I'm going to do one thing is usually happening in this kind of promotion. Please subscribe, like, forward, and comment us. Thank you so much for your listening. I'm keeping in this screen for a while. So if you want to take notes, just do it. Thank you so much. And I'm done. So is there any questions?
Thanks, Jingyi. I think we'll pass over to Amy now, just so we can stay on time.
Sure, thank you.
But if anyone has questions, please post them in the chat. Amy, we don't have sound for you.
I said I was scared to use PowerPoint now because everybody had so many problems. So I'm like, uh-oh, I guess I shouldn't do that. Okay, so let me just zoom in a little bit. And let's see. Let's see if I can just zoom in. Okay. Can you see this okay or no? It's kind of a little, now I'm using Word, which is probably as problematic. Let me just zoom in a little bit. Okay, I think that's good enough. So Sinead asked me to give an update on the video that I'm putting together. So I'm making a video about the activities specifically from the summer for USAfri. So that's the research collaborations and the virtual ones as well, and the research visits, and also some of the activities at the Electronic Structure 22 workshop, which is happening next week, and you will see a lot of the same faces. And then I asked Sinead and Richard if I could give a plug for my personal project, which I'm hoping I can get some interest from you all here. I'm making a documentary series about the redefinition of the kilogram, and I've received questions from people. How can you even make a short film about that? What is there to say? It's a 9-episode doc series about it, believe it or not. And I am very interested to talk to people from African nations who either teach the new definition or they have incorporated the fixing of Planck constant in their research or their teaching. Or you have strong views about metrology, or you have strong views about Planck constant. I didn't know people could have strong views about those things, but actually I live with somebody who does. So I'm very aware of that now. You can email me either at my University of Illinois address or at the US Africa Initiative Gmail address. It's me. I answer all the emails there. I've probably been emailing you tons there. If you are interested in talking to me and you are willing to possibly be in my documentary series, you can speak any language you prefer. I have people who speak French, German, Japanese, English, what else? Russian, and so forth. Spanish. So there's a lot of languages there. I include a couple of still frames so you can see the kinds of things that I talk about in the film. These are the equations on the floor of the National Academy's Science in Washington, D.C. There's NIST. If John Vinson is here, he will recognize some of this kind of lab work that they do. That's the scene of the weighing of the heart from the Book of the Dead. We have an expert who talks about that weighing in psychostasia. Also, this is this person in front of this kilogram. That is Michael Glaser at PTB in Braunschweig, Germany. And then I filmed at the National Archives of France. That's a replica at CNAM. It's a stainless steel replica, and also platinum. I try to contrast, you know, items made for the nobility with the kilogram, which was disseminated and intended to be for everybody. And then if you're familiar in Paris, you might have been to this marble wall monument, the standards that they installed in Paris in 1790s. So I'd really love to include people from the African nations in this project, and I don't have anyone so far. I'm really interested, so I'd love to hear from you. Please don't be shy. Again, you can contact me at either of those email addresses. And even if you don't care at all about it and you'd like to just say, I don't have to incorporate any of these changes in my curriculum or my research, that's still valuable to me. So I just love to include somebody, different people from the African nations. Also, let's see, Latifa had said she wanted to make contact with someone from this meeting, but she wasn't able to grab them in the chat, in the Zoom chat. So this is back to the meeting's purpose. If you would like to make contact with somebody, I'm always happy to help make contact for you and get you started talking. I've done that in the past. And again, just email the USAfrI Initiative Gmail account or email me at the AM Young account. I'm pretty much always on email, as people know, and I'm always happy to help make connections for people who want to get together to talk about their research. So that's it from me. Thank you.
Great. Thank you so much, Amy, for the past 5 minutes, but also for all of the work you've done for USAfrI so far. I think you deserve a special call out, apart from the thank you you'll get later as well, I'm sure. I think everyone has, I think every single person in this call has had at least one email from Amy, and she's been doing so much more in the background that you haven't been able to see. Okay, so not to run over time, we're going to get started on the final event other than the closeout. So Richard, I'm going to pass over to you to do the introduction for Dr. Matteo Rini. If Richard is there, he is. Okay. And Richard, you're on mute in case
there we go.
Yep, there we go. Okay, great. Thank you, Richard.
Fine. Can you give me just 1 minute?
Sure. I guess, well,
I was doing something and I thought it was a little bit later that I was supposed to do the introduction. Okay, I'm almost ready. Hello, everyone. Oh, it's a real joy to have Matteo Rini talking today. He'll tell us about communications. This is something that's a really wonderful addition to this workshop because it's something we need. At the assessment schools, it was one of the extras that we would always try to add in. It was almost a second afterthought because it's been so much time figuring on what are the research things to talk about, etc. But in fact, communication is one of the most important things in science, not just our field, but science in general. So Matteo Rini is an editor for a physics magazine for the American Physical Society. He holds a PhD in electrical engineering from the University of Pavia and a PhD in physics from Humboldt University. So he's well versed and you know, been around. And he was a postdoc and research fellow at the Lawrence Berkeley Lab. And I got to know him at APS meetings and just sort of accidentally finding out something about him. He's a really fine person to know, and it's a joy to welcome him to talk to us about communications and how to communicate what you're doing and how to communicate science in general. So, Matteo.
Thank you, Richard, so much for the very nice introduction. It's also really nice to meet you and to chat about communication science Africa. It's really amazing what you're doing for this initiatives, and I really appreciate it a lot. Just a question for the organizer. We are supposed to finish at 12. How long do you want me to speak? That wasn't super clear to me. 45 minutes is okay?
Yeah, Yeah, we're a little flexible on time, so it would be good to have some time to answer questions. But yeah, you have about an hour. Yeah.
Okay. All right. Sounds very good. So let me share my screen if I can. And you can hear me well, right? The sound is okay?
Yeah, perfect.
Great. All right. Thank you, everybody. Thank you for being here. I see you're very numerous. It's amazing to have this, so many people interested in communication. I totally agree with Richard. This is something that we rarely think about when we do our research. And I guess I will argue in this talk that this is a very, very important aspect of science, and we should really think about it a bit more than we do. As Richard said, I am the editor of Physics Magazine. It is a sort of a popular science magazine of the American Physical Society. I will tell you a bit more about what we do there. But I'm also a professor of science writing and communication at NYU University. And so there I teach a class that's really focused on writing scientific papers, giving good presentations, and writing PhD theses. So it's really focused on doing practical things that help you improve. So my talk today is based, I guess, on this two experiences, and I will try to give you both some very practical ideas and suggestions on things that you can do to improve your writing and communication skills, but also some very sort of fundamental and philosophical thoughts on that. And I would like to start with the take-home message. I think I like, just to leave you with one thing. So if you fall asleep and you want to bring one thing home, I think it has to be this. This idea that if you are a scientist, you're also a professional writer and communicator. And I guess this is something that we sometimes do not realize. Maybe I see, scientists, I talk to a lot of them, I go to conferences, and they are, always ready to do a lot of things to carry on their research. They're ready to learn how to align a laser, to program in some language they need, to operate an instrument, and they're ready to spend weeks there to improve the skills. However, I see that quite a small number of them really spend time thinking about their communication skills. And I think that really, if you want your science and your research to matter, it will not speak for itself. You will not be able to convince people of how beautiful it is, how important it is, why you should get funded, unless you can communicate it well. So I would argue that, again, if you're a scientist, writing, communicating is really an integral part of your work. And so we should treat it as professionally as we do with anything else. And as many things we do professionally, we learn them on the job. So I'm not arguing that you should take a class, or if you can, that's wonderful. But what I'm suggesting is that you just simply think about this responsibility that you have. You have to communicate what you do, and you have to do it professionally. So every time that you're doing, every time you're giving a talk, every time you're writing a paper, every time you're communicating what you're doing, try to learn from it, try to improve it, try to become better at it. And you will see, a constant and steady progress. And I think this will benefit your science. This will benefit everything that you do. So I would very, very strongly argue that you should just think about this responsibility that you have. So if you want to have this profession of a scientist, you should also consider yourself somehow like a professional writer. You're Einstein, but you're also Dostoevsky, so to say. And I'd like to spend a couple of words on my path, just to give you an idea of where my thoughts come from. I was, a laser physicist, and for about 10 years, I was basically doing this. This is, of course, not exactly what I was doing. This is a stroboscopic photography experiment that was done over a century ago in Stanford. And the idea of this experiment was to study how a horse is galloping, and whether at some point in its motion, its four hooves, its four legs are off the ground. The motion of the horse is too rapid for us to see, and so you need some technology to be able to see this. And what this photographer, Edward Muybridge, did, it's actually both a piece of art and a piece of science. He basically developed this technique where you're taking a series of snapshots and you can reconstruct from the snapshots how the horse is moving. And as you can see from some of the panels, indeed the horse, like the panel number 3, indeed the horse at some point it's flying. And so it's actually funny that this sort of piece of art and science had an important impact in art, because before, if you look at paintings from the 19th century, horses were depicting galloping with their legs extended to the front and to the back, but that's not how horses are galloping. So this was a piece of technology, but at a profound impact on art. And if you look at paintings about horses galloping, you'll see they are depicted in the right way after this photography was published. But of course, in the 21st century, we're not doing this with a camera. We're not looking at horses. But the principle of the experiments that I was doing were actually super similar. I was doing stroboscopic spectroscopy, so I was taking snapshots of how molecules move when they are in a liquid, when they undergo chemical reactions. What we did was what is called a pump probe experiment. You have 2 laser pulses. The first one sort of kicks the horse and tells it to gallop, so it starts a chemical reaction. And the second laser is an observing laser that looks and takes snapshot at a given moment. So you can change the delay between these 2 pulses, and the result is that you take a series of pictures as a function of time. And so from this, you can reconstruct the motion of a chemical reaction. You can try to understand how chemical reactions are happening, and so on and so forth. So I did this for a long time, and I was actually decent scientist, probably a very lucky scientist. We published this work in Nature and Science and Discovery Letters. I think the most important thing that I did, if I have to choose one, is this study of acid-base reactions, one of the most ubiquitous reaction in chemistry and biology. It has a lot of industrial applications. And thanks to this technique that I was talking about, we're able to measure how long it takes for this reaction to take place. And this was published in Science, and a very big echo. So everybody at that point was expecting me to just continue, get a professorship and do science. But I had an interesting summer experience that sort of changed the rest of my career. I went to work for what is known as the European Commission, sort of the government of the European Union. There's an ensemble of countries in Europe. And I was there as a scientist trying to help politicians and policymakers with some questions, with some decisions that need some science as a basis. And I was there, I was working on climate change, I was working on energy issues, I was working on trying to define where the money of the European Union should go. And when I started working there, I had the sort of presumption that, we scientists, we are the people who know how things work, and just politicians are not so smart, and they may not get it. So the problem is with the politicians. So we just have to make sure that they listen to us. But very quickly, I realized that the big problems was also on the scientist part. And I had a quite a revealing experience one day. There was a nuclear scientist, a very prominent and famous scientist, who came to the European Parliament to lobby for funding for their research. And basically, he had 5 minutes to talk to these politicians, most of whom have a background in politics, in humanities, they're lawyers, and so on and so forth. So very little knowledge of science. So this person had 5 minutes to talk about why you should fund nuclear research. And in 5 minutes, he said four times, I kid you not, he said 4 times quadrupolar moment, which obviously is not an expression that any politicians could relate to. I mean, I can barely relate to it, so I cannot imagine what they would have felt. So it was a big missed opportunity for him to make the case. The funding didn't go very well. But it's not just this 5 minutes that matter. There were many other factors. It was just after Fukushima. So many things that shaped that decision, but certainly he missed an opportunity to make the case for that. And so I realized more and more that this behavior on the part of the scientists actually had a profound implication on the society and policymaker. And I realized that, I thought that politicians will look at us scientists and think, yeah, we are doing very important things, we're doing very beautiful things, we should fund them, we respect their opinion. But I realized that when they look at us, when they look at these people coming to speak to the parliament, that's what they saw. They saw this kind of pictures, people who are old and white and maybe some sort of dangerous, and all these representations of scientists in the media have one thing in common. These people do not speak like normal people. They do not communicate well. They are coming from the sort of aliens coming from another world. So I decided to try to address these issues, and that's what made me start to think about how important communication is, how crucial it is to how science is done, to how science is funding, to how science even progresses. And so I decided to steer my career to that direction and to just focus on these issues. And that's when I became the editor of Physics magazine. And just a few words, this is an online journal of the American Physical Society. It's sort of a popular science outlet. And I like to just bring out a couple of things that I do for this magazine because they're important to what we're going to say next. I think the most relevant thing that we do are they're called viewpoint articles that cover the most important stuff, the most important results in contemporary physics. Here are two examples. One of them is the famous LIGO experiment, the discovery of gravitational waves back in 2016. The second one is one of the last paper by Stephen Hawking, who's trying to improve on his discussion of the black hole paradox. And so what I do for this articles is I work with a scientist and I edit them and I try to make their article accessible to every physicist, to every scientist. So I think that's I guess it's the experience that mostly teaches me how scientists think when they think about writing. And so that's what I'm going to use for the next talk. And just to spend a few more words about physics, we actually cover Africa quite a lot. This was a beautiful opinion piece by Netaya Chetty of Wits in University in South Africa. This was another collective Q&A with a bunch of African researchers, South African researchers. We are also exploring sort of creative ways of communicating. This is a cartoon. If you have heard of this mu on G-2 experiment, it was sort of big news last year. Very complicated physics, and we asked this famous cartoonist, is known as PhD Comics. He's a wonderful, wonderful artist, and I think this is the simplest and clearest explanation of this complex result that I've seen. And so I really recommend that you take a look if you're interested in this kind of physics. We're also launching a podcast, so we're playing with many ways to communicate physics. But let's focus on writing. And I guess for the last part of my talk, I'm just gonna try to give you some thoughts on how you should write your papers. And I like to focus on that, although many of the principles are really applicable to presentations or to writing a PhD thesis and so on and so forth. And first of all, I guess you should ask yourself, why should I write well? And I think when I give the seminars, when I visit universities, people have one thing in mind. If I write well, I'll get more papers published. And I think to some extent this is true, but I think there are so many other reasons why you should write good papers. And I think that one of the most important ones is to get cited. Your paper actually do not matter because they appear in Nature or anything else. They matter because they get citations. They matter because they get read. And citations are actually one of the most important measurements of a scientist's success. You probably have heard of the H factor. So this kind of metrics depend on how cited are your papers. So they don't care whether your paper are in high impact journal, but they care about the fact that your paper has been cited. And you get cited, and I can tell you, I've done a lot of analysis of the most cited papers, and one thing they have in common is they're super clear. They're written in a very nice way. You can imagine a lot of people reading them, learning something from them, and then deciding to cite them because they have taken on something from those papers. Another very important aspect of writing well is for your research proposals. You want to get your proposals funded, and when you submit your proposals, you have to think about who is reading them. Something I will talk about later on a bit more, but when you're trying to communicate the key principles, that you have to imagine who is on the other end. So it's a two-way process. It's not just that you are speaking about what you've done. And so if you're writing a proposal, you have to imagine who are the people examining your proposals. And most of these program managers, funding agents, they are people with a very broad portfolio of work, and they will not know the details of what you're doing. So you have to really write in a very accessible way for a broad audience, for somebody who is a scientist, who is a physicist, maybe who's working in your field, but not necessarily on your topic. Another important aspect, I think, that is actually essential for the progress of science is that you, by writing well, you can communicate with scientists from other fields. And I see more and more the breakthroughs that I'm reporting on for Physics Magazine, for instance, very often, I think increasingly, involve connections between different fields. For instance, there are some very abstract theories that were initially thought for particle physics that are being applied now today, and probably being in this field, you're aware of them. This ADS CFT correspondence, for instance, particle physics idea are being applied to condensed matter physics. And of course, to borrow these ideas, you need to be able to read those complex particle physics papers and get something from them. Maybe you don't get everything. You will not get the details of the theory. You may need to call up the scientists, write them an email to start a collaboration. But these ideas do not appear to you unless you can decipher those papers. And so this interdisciplinary communication, I think it's really essential for the progress of science. It's not just about PR, publicity for your paper, getting cited. I think it's really an intrinsic element that helps science advance faster. And another aspect that I recently discussed with some of my students at NYU, yes, it becomes easier for them to write papers. Also comment that somehow the very act of communicating what they're doing, the very act of thinking about the structure of how they're going to explain what they're doing, helps them structure their research too. So I think if you write well, there is some sort of feedback mechanism that will also allow you to do better research. And finally, a lot of you I know are pretty young, early on in your careers, and you may not even be sure, do I want to do physics for the rest of my life? Maybe I want to just do marketing, work for Google, why not? Communication skills are actually important in any career path, in anything you're going to do in your life. So if you work on them now, you will have some tools that will help you no matter what you decide to do later. Actually, some of the biggest supporters of our communication class at NYU are actually companies who say the one thing we want people to come out of this school with is the ability to communicate. And so they were some of the biggest helper in making this class them giving happen. Let's go back to now. Let's get more concrete. What you can do to write. And again, I want to connect to two things that I have to do for Physics Magazine. The first is to find the best science. So how do I know that a paper is worth writing about? And the second is to communicate it. So finding the best science. I'm reading literally hundreds of papers every week. I've got to become very fast in assessing them. It's a huge workload. And so I realized that, when I read an abstract and I read a paper, I want to answer these 4 questions. The first is, why this research? And this is typically done decently in most papers. You know, what's the holy grail? You want, for instance, to develop solar cells that are cheap, affordable, robust, and have a large efficiency. So that, you know, that's the holy grail, the ultimate goal. You may not, you know, fulfill this holy grail, of course, in every paper that you're publishing, but that's what is driving you. So the key, big motivation, the dream that's behind the research. The second is the open question. So within that holy grail, what are the specific research needs? Some really concrete open question that your work is going to address. And that is crucial to show that your work is novel and adds something that is worth learning about. For instance, if we keep that solar cell example, you know, we may want to develop solar cells. There might be a particular technology of cells, for instance, perovskite solar cells are all the rage these days. They are very efficient. However, people haven't figured out really how to put them in the environment without them degrading very soon. So the open question that you're working on is how we can take this specific class of solar cells and make them last longer when you put them out in the sun and in the weather. So that's really the specific question that you connect to. And then, of course, you're going to talk about the key results, and most papers do this pretty well. What is really new here? What is the one thing that we need that wasn't known before? And finally, and I'm always surprised that there are some papers who do not cover this aspect at all. What are the implications of this result? So you found something. So what's going to happen now? How is this going to change future research? How is this going to impact technology or the society? And a lot of papers that I'm reading simply do not discuss this at all. And I guess the assumption is that they know already what the implications might be, and they imagine that everybody would know. And of course, if you work in that specific field, you probably know you found something and this is why it matters. But if you don't tell the reader about these implications, they will not know. And sometimes I read something, you know, it looks exciting, it looks intriguing. We measure this parameter with a precision that is unprecedented. But then I ask myself, why should I care? Why is this helping anything? And so think about that aspect. And then the second part of that, you know, 2 things that I want to talk about is I have to find good science, and then I have to help scientists communicate it. And so in this role, I have edited hundreds of scientists, and they send me their drafts, and then we work together to improve it. And it's a long process, and I guess it gave me a lot of insights into what are the worries when they're writing, what are the mental processes when they're writing. Sometimes it's not so easy, and I'm going to share you some emails that I received, from emails that I received from some of the scientists. The first is saying, you're simplifying too much. They'll think I'm stupid. So to this person, being simple equals being stupid. He wants to make things sound complicated because if they sound complicated, people think that this is someone smart. This is an important paper. The second one is writing, if a scientist does not know what a Lyapunov coefficient is, he and you should just go back to school. I'm not going to waste time explaining. So they really cannot imagine that people do not know this pretty technical thing. Maybe you've studied this in statistical mechanics or in mathematical classes, but you might have forgotten. You're working on something completely different. You're not using statistical theories. You forget what a Lyapunov coefficient is. So does it really, is this a big deal to define it? But so this person defining it was, you know, was really almost humiliating. It was trying to define something that everybody should know. And the third says, you've massacred my text. Once again, there is no way to explain this without Hamiltonian equations. So he would, to him, it was just impossible to figure out an explanation. It wasn't based on equations, but that you know, that was more intuitive, that it was simpler. And so I think this email sort of reflect the challenges of science communication. And I think the most important ones are these ones, the ones that I find. And I think they all come from the fact that the environment in which we live and work in physics is not really conducive. It's not really stimulating you to try to communicate well. And the main problem is that you're always communicating with your supervisors, with your competitors, your colleagues. Sometimes a joke with professors at NYU, you know, and with students, I tell them your supervisor is actually the biggest enemy of your writing. And the reason is that when you're writing your papers, you're trying to communicate to your supervisor. You only have that person in mind. So as a result, you're talking to somebody who already knows everything. They know why you're doing this. They know why it matters. You're talking to impress that person, to be evaluated. So you want to sound complicated and sophisticated. You want to sound academic. And you're spending a lot of time communicating the how. How did you do the experiment? How long did it take? What were the problems? But you forget completely to talk about the why and the so what, which are two super important parts of the research. The other aspect, if you thought about that person's telling me, you know, I don't want to define Lyapunov coefficients, is what I call the curse of knowledge. You spend so many years working on something that you forget how it was before you started working on that thing. You forget how you were. You forget the words that you didn't know. So you think that everybody will know the words that you've learned, the jargon that you've learned, the concepts that you've learned. And so you have that curse. Your knowledge is a curse because it brings you to forget that some people may not know. And the last challenge, I think it's sort of the general challenge of communication is not relating to the audience. So you're not really thinking about who is the real audience right there, reading your paper, listening to your talks. And so I think one has to work with these challenges. And in the second part of my talk, I want to talk about this. So how to overcome these challenges and just some general idea. The first part is to write with the reader in mind. If you're giving a presentation, to talk with the listener in mind, and you know, think about who really is reading your paper. It's not your supervisor. It's not your competitor. Your paper will be read by hundreds of people. Young students starting a PhD, research some other field, trying to get something from your papers. So try to get a realistic picture of who is actually there. And try to make the paper somewhat accessible to them too, and not just to your supervisor. The second thought is a lot of people, when they come to these classes, they think, oh, I'm born a writer. Some people are just good. They just give talks and they're great. What I can tell you is that if you know somebody who writes very well or gives exceptional talks, this is because they practice a lot. And this is because they improved. It's almost never a case that it's some talent that you're born with. So I really see how practicing changes people's skills. And so if you want to learn how to write and communicate well, practice a lot. And a good way to learn is by reading. So read a lot, read everything that you can. It's something I was not doing when I was doing my PhD, but put your hands on as many papers as you can. Try to get a picture of what's happening in your field and beyond. And if you find a good paper that tells you something, if you find a good paper that excites you, that you learn something from, focus on what are the ingredients that make this paper able to do that. And trust your instincts. If the paper is good, it has to have something. So try to see, how did they write the abstract? How did they structure this paper? How did they answer those 4 questions that I was talking about? The why, the open needs, the so what. So try to focus on what makes that paper special and easy and accessible to you, and try to learn from it. If you think about novelists, they are the greatest novelists because they've read any single novel that's been published before them. So do the same, read and learn from what you're reading. And again, an essential concept of communication I'd like to emphasize is that communication is not a one-way street. You're not just telling people what you did. You have to somehow get cues. And even when you're writing, you have to think about who is on the other end. and who is your audience, and develop empathy for them. Put yourself in your shoes. Imagine that you are, say, a biophysicist reading your papers. What is they wouldn't learn? So try to think about the audience. If you're writing for a very high impact paper, writing for physical review letters, your paper should be accessible to every physicist, no matter what their field is. So try to put yourself in the shoes of somebody coming from another field, accessing your paper. You really have to make it accessible to them too. And one thing that we do, I don't know whether this could be done for this kind of initiatives. One thing that we do at NYU, we actually do what is called an improvisation class. We have actors that come in and play with the students and ask them weird questions like, explain your research to somebody who's traveling from the Middle Ages. So the time travelers who come here, and you're trying to explain to them why you're studying strongly correlated electron systems. And so that exercise, which may sound extreme, but allows you to develop that instinct, like who is that person that is receiving my communication? How can I help them? How can I try to feel empathy for them and use words that they can relate to? And another little point that I want to make here, maybe not all of you are native speakers of English, and I like to emphasize that there is little, or I would say zero, correlation between speaking well and writing well. Writing a good paper has nothing to do with not making mistakes. It's nothing to do with grammar. Actually, when I edit scientists, some of my favorite writers are non-native speakers. They send me drafts that are full of errors, but that doesn't matter because the errors can easily be corrected. What is harder to correct is whether the paper, if the paper doesn't answer the full questions, doesn't give the reader the elements, doesn't have a logical structure. So I think this is what makes a paper good: the logical structure, the clarity, and so on and so forth. And grammar has very little to do with this. So if you're not a native speaker, it's not an excuse for thinking that you may not write well. If you're a native speaker, is not enough. Writing is about other things. So let me get a little more concrete. And I guess when I work with scientists, I follow a structured approach to writing, and I'm going to tell you a little bit about this. These 4 elements. The first one is finding your story. The second is devising a structure that tells your story, and the third is to apply effective writing strategies that allow you to tell that story with the structure that you have in mind in an efficient way, in an accessible way. And so in the last 20 minutes, I'm going to talk about this sort of structured approach. The first thing is, I strongly believe that writing is storytelling. So every paper is telling a story. And what do I mean by that? It's not just telling, what you did. The story is these 4 questions that I was talking about: why you started doing that research, what kind of questions were you trying to answer, and what you did to answer them, and finally, why do your answers matter? What will they impact? And just to clarify this, I'm going to give you sort of an extreme example. This is a very famous paper by Rosalind Franklin on the X-ray diffraction pattern from DNA. So this paper was part of a pair of papers. This first one was presenting the data. And I like to contrast telling a story with presenting data. The paper shows you what happens if you shine X-ray light on DNA, and that's a diffraction picture that emerges. And from that picture, so this is presenting data, but telling the story is actually this, what Watson and Crick did with this data. And they show that DNA has a helical structure. And I guess that's very important, of course, because of the genetic copying mechanism that this structure implies. And so that is the story that was behind this data. So think very carefully. Are you just presenting, the 2,000 things that you did in your experiment, or are you trying to extract a story from these measurements? This is an extreme example. I mean, it's also a bit inaccurate. I don't want to say that there was any mistake on Rosalind Franklin's part in presenting. That's how they arranged it to be. But I think it might have played a little part in the fact that Watson and Crick probably unfairly are given credit for the discovery of the helical structure of DNA, and Rosalind Franklin did not get as much credit. And maybe that's because she was presenting the data, and that they had the role of telling the story that they could extract from this data. And one thing I'm really convinced about is that every paper should tell not more than one story. Sometimes I get these cover letters from authors submitting a paper to a physical review, and they list 7, 10 reasons why you should publish that paper. Not only we discover a device with the highest efficiency, but this is also interesting at the fundamental level. And by the way, so they list a number of aspects. And I can tell you, when an editor, be it physical review, Nature, or Science, says the oldest list of reasons to publish, if any individual reason is not sufficient to publish it, they will not publish it. It's not that by putting them together, you're making the case for publication. So try to focus on that one story, the one thing that you want to tell people. And one thing that I always suggest is to brainstorm before writing. Try to get that story, try to make that story emerge. What is the one conclusion, the one take-home message that you want the reader to know, the one new thing that makes your result better than anything that's come before? So when you're writing, the story may change. So keep asking yourself during the process of writing, what is the story that I really want to tell? And a very good exercise is to write down a 2-line summary of your story. Is that summary clear and sharp? Can you come up with a very short way of presenting the story? And here are some examples. Take a look at the last one. A solid-state optical memory stores a light pulse and even a full image for more than 1 minute, the longest light storage time reported in any system today. This is how your story should sound. And a very good use of this story summary is in a cover letter that you are sending to the editors of a journal when you're proposing a paper for publication. You write to them, dear editor, I'm going to submit this paper. This is what we did, and there comes your story. So try to crystallize that story. Once you have that story, you should build a structure that tells that story. And there may be different ways of doing this, but I think that what really works for 95% of the papers is this classical structure that starts with a context, the broad why, the research needs, a more specific why, what we did and found, the how, really the core of your work, the actions that you took. And as I said before, the implications, the so what. And that's a very big shortcoming, I would say, of probably the majority of papers. These implications are not clear. And so as a reader, you're left with the question, why should I care? So try to answer that question. And a very good way of tracking the structure of your paper is to use an outline. So when you're writing down your paper, have an outline on the side, Word can generate it sort of automatically if you use header. This titles and headers will maybe not be part of your paper. Some research journals don't allow it, but it will be a great guide for your writing. And one thing that I like to emphasize is the importance of paragraphs in the writing. This is a citation from some great teachers of writing. This is a good book. Make the paragraph the unit of composition. So the paragraph is sort of the atomic unit of your paper, the atomic unit of the logical flow of your paper. So each paragraph, a lot of people think we're writing a paragraph, it's long enough, let's start a new one. That's not what should happen. Each paragraph should tell a coherent, complete story. So think about what is the one, again, mini story that you're telling with that paragraph. What is the one unit of thought that you want to communicate with that? And a great technique to write good paragraphs is to use what I call a focal sentence to reveal that story that each paragraph is telling. And there are two important options, a point first paragraph and a point last paragraph. The point first paragraph has this sentence at the very beginning. And basically, it sort of gives a preview of what the paragraph is talking about. So let's take, this is a paragraph from LIGO, from that famous discovery of gravitational waves. It starts by saying the basic features of this number is the name by which they call the event, pointed to being produced by the coalescence of two black holes. And then they describe these features. But as you go on to read these features, you already have the conclusion in mind. These features point to it being produced by the merger of two black holes. So you can process the information that comes next, all the details. It was actually a much longer paragraph that talks about frequencies, that talk about the waveform of the signal and so on and so forth. But prepare that so that you guide the reader and you give them sort of an anchor by which they can interpret everything that comes next. Another option that may be more suitable for different kinds of paragraph is to have it at the very end. In this case, for instance, they present a number of results and then they wrap it up by saying, concluding all these measurements put together tells you this. And again, this helps you sort of collect all the information that you got and prepares you for the next paragraph, so that the logical flow is clear. So these focal sentences that point first or point last are a great aid to writing a paper. And I think that thinking about them will really lead to big improvements in how you can access the paper. And finally, the third part, and spend 10 minutes on this, is to think about effective writing strategies. And so you come up with a story, you build a story structure you think is logical, makes sense. And now how can you tell the story in an optimal way? And here's some thoughts. And I guess the first one is connected to what I was saying before. You don't have to make your writing sound academic. You don't have to speak in a stuffy manner for a judgmental audience, that is the audience of your supervisor. Try to be simple. The simpler, the shorter, the better. There is this principle in science called the Occam's razors. If you have two theories that explain data equally well, you have to go for the simpler theory. I think Occam's razor applies to writing as well. If you have a shorter formulation that gives the same amount of information as the longer one, you have to go for the shorter one. So this is a citation from another writing teacher, William Simpson. The secret of good writing is to strip every sentence to its cleanest component. So everything that shouldn't be there, every word that is not really necessary, is actually an adulterant. It's something that makes your writing less understandable, less readable. So try to cut it. And some thoughts on economy and lightness. And I'd like to start with the first one. I think is a great example. I'm handling a lot of papers. I'm writing about a lot of papers to study bird migration these days. There seems to be some crazy quantum mechanical effect at play that helps birds, the spin of the electrons and such, helps birds navigate in Earth's magnetic field. And one thing I noticed is that these papers, they cannot call birds birds. They want to use the avian species. And why are they doing this? I asked myself. And I thought maybe actually the avian species is something more general than birds. There's some difference, but no. The truth is birds are the avian species. The reason why they're using 3 words instead of 1, a more complicated expression instead of an everyday one, is that because they want to sound academic. And I really think that shouldn't be the case. We don't have to aim for complexity. We don't have to aim to sound difficult. Simple is better. So don't have that instinct of trying to make things more complicated than they are. There are some sentences that are, the second example, are completely unnecessary. This is a sentence that I encounter very often at the end of the paper. This work sheds new light on the physics of strongly correlated systems. Why is this useless? You read the paper. This word sheds new light means it's telling you something new on the physics of strongly correlated systems, basically on the topic that you know this paper is about. So this sentence is basically just telling you, this paper is actually telling you something new in this field. That's all it tells you. So if you want to add something useful, say what that new light is, but just adding the sentence is not really adding any information. Another common thing, adverbs are often useless. What is the difference between something being very large and large? If you conclusively demonstrated something, you demonstrated it. If it's not conclusive, you didn't demonstrate. You should use another verb. But very often the adverb is contained in the verb. So these are some of the thoughts, and I'll give you a reference at the end of my talk of a really nice article that can point you to some of these problems and help you find solutions. And probably I won't go into these details, but another common thing that I see people doing, it's something that I used to do when I started writing, is to try to make my sentences as long as possible. I thought that was showing that I had mastery of the language. But take a look at this one. You read it: techniques for the direct phase modulation of laser diodes, typically based on the control of the applied current or voltage and always associated with a very dramatic amplitude and or frequency modulation of the emitted light, have been available for decades while being insufficiently reliable for high bitrate communications and quantum key distributions applications. You can barely breathe, but it's not just a matter of elegance. It's really hard to read this and get the message. This sentence contains 4 or 5 ideas that they want to communicate. So the solution is break it up. Techniques for modulating the phase of laser diodes have been available for decades. They're typically based on the control of the applied current and voltage. However, because such methods are always associated with this, they are unsuitable for that. So use short sentences. It will greatly improve the readability. Some other example, again, I will give you a reference to this. Clunky phrases that you can make simpler. And again, I think you just have to fight that instinct that it's sort of natural because that's the world you live in. You want to sound scientific, you want to sound academic. You tend to pick a clunky phrase just because you've been exposed to clunky phrases. But think about that. And again, the reference is going to give you some ideas. And another very fast thought that I had is that we really need to depersonalize science. And I would really argue that we don't. And I've seen some examples in the literature. First of all, use we and I. There is a lot of passive voice in this paper. This has been measured. Why don't you just say, we measured it? And I can give you an example. Einstein in this paper, habe ich gezeigt, I showed. Back then, it was sort of normal to use the first person. And we are sort of trying not to do it anymore. We're trying to be impersonal, probably because it sounds more objective. But you are the agent doing the research. So use active voicings, not passive. Use the first person. Use we or I, if appropriate. Sometimes some creativity, and just, I'll leave you with the slides if you're interested, but this was a paper in a review of modern physics, yes, I see a message. Yeah, I will share the slides definitely. Review of Modern Physics is the highest impact journal in physics in the world. And this was the initial title, and you can read it, and it's really not very informative for somebody who is not in the field. And that's a title they came up with, Diabolical Conical Intersections. That's pretty impressive. It's like, just communicates the thing. If you are an expert in the field, you know what conical intersections are. And diabolical just tells you they're very complicated because that's where the Born-Oppenheimer approximation breaks down, and you cannot describe electrons and atoms in a separate way. So this very compelling title contains it all. It's very accurate, but it's also very beautiful. And I think it's a part of the reason why this paper is one of the most cited papers ever. And some other expressions is just, let's take a look at this one. The difference between the 2 types of variables can be elucidated by describing 2 ways of watching fish. In the linear picture, one stays at the point, watches whatever fish happens to come by, and in the Lagrangian picture, you pick a fish and you follow it. Very simple way you can relate to. And suddenly I understood what the difference was between the Eulerian picture and the Lagrangian picture. So use this everyday comparison. Don't feel that you have to make it sound complicated, stuffy, academic. Use some humor sometime. It was a good example here. Radiative fluxes from this star are still short, this is long, even compare, short, changing the time scale, short compared to your journal publications time scales. It was a pretty funny statement, I find. Anyhow, so be light, be short, be concise. Another important thing is we always think in terms of visuals, and figures are a very important part of the paper. Build your paper around the figures. Take your figures out when the paper is ready and try to present the story in your paper using the figures and in the captions. if somebody just looked at the figures, and I can tell you, many journalists, many editors, many even scientists, many funding agents, when they're reading a paper, they read the abstract, they read the title, and then they go through the figures and think if they got the story just from the figures. You have to allow for this access. So build your figures carefully, analyze them separately, and try to ask yourself, am I telling the story with the figures and this caption? And if not, you should probably revise it. And another concept that I want to talk about very quickly is multiplicity. So I said, you are not writing for your competitors, you're not writing for your supervisor only, but you're also writing for them. So your paper does not have a unique level of access. Your paper should be tailored so that you can speak to multiple types of people. Somebody who is not an expert, there is no way that they're going to understand the core, the action, the experiments, the details of the theory. You don't want them to read that, but they have to understand the abstract, they have to understand the introduction. So design your paper with an accessible abstract, introduction and conclusion, accessible to everyone, and then it goes a little narrower. The first paragraphs, they may be accessible to researchers in a related field. And finally, the conclusion, it goes broad again. Of course, there will be some parts of your paper that are only really speaking to people who are working on exactly that same problem, the numbers, the details. So you can talk to all of them at the same time. So look at your paper and try to design different levels of accessibility, different language that you use. But always focus on the first part a lot, the abstract and the introduction. They have to be really broadly accessible. And one metaphor that I use a lot is that of an hourglass. Your paper is like an hourglass. It starts very broad for everybody. It goes narrow. And one thing that a lot of people forget is it has to open up again. The conclusion of the paper should become very accessible again. And I'm just wrapping out now, and I like to emphasize 6 values that I think writing should have in all its forms, be it literature, be it science paper, everything. And this is actually a memo, a handwritten memo taken from a fellow Italian writer, Italo Calvino, one of the most important writers of the last century. He was coming to Harvard to give this series of lectures called the Charles Eliot. He was going to talk about 6 values that the writer should have for the next millennium. That's how he titled the sequence. And I like to refer these values to science writing because I think they're actually the same that we should strive for. The first is lightness. Your writing has to be as short as possible, as light as possible. Don't make it more complicated than it should be. Quickness, conciseness, don't make it longer than it should be. The shorter version is always the better version, unless, of course, you're losing information. Exactitude, I refer that to the logical flow. Design the logical structure of your paper so that it's flawless. It has to answer these 4 questions, and it has to be very logically organized, that don't have to be repetition, so focus on that. Visibility, the use of images is very important. Make that count, make your pictures count, make your figures count, prepare them well. Multiplicity, as I said before, you have to make your paper accessible from multiple levels for the most expert, but also for the non-specialists. And there are ways to do this so that you can speak to all of them without losing any of them. And the last memo, unfortunately, Calvino died on his way to Harvard, so he couldn't give his last lecture, but he called it consistency. So I don't have any text. He didn't prepare it yet, so I can only imagine or speculate about what he was going to tell. But so this is my take on it. And I want to recall what I said at the beginning of the class. If you are a scientist, you are a professional writer, or maybe to put it broadly, a professional communicator. So try to be consistent when you're communicating, when you're writing. And every time you do it, think about how you're doing it and take that responsibility. You are doing this, and it's an important part of your profession. So try to think about whether you're doing this in an optimal way. So if you do this regularly, this consistency will actually allow you to improve. You will slowly recognize the passion that you put in your science, in your talks and in your papers, You recognize the clarity of your thoughts reflected in the logical structure of your paper. And I think in a few words, this is that the conclusion is that you will find your own voice in your talks, your own voice in your paper. That will be yourself. It will be much more fun for you, and it will be much more effective. So try to just spend some thought every time you're doing it. So thank you very much. This is my email. I will share the slides. Feel free to contact me with any questions. Just briefly like to mention there's two resources that I think are amazing. The first is an appendix, a review of modern physics. It's called Writing a Better Scientific Article. It has some really practical thoughts on the things that I mentioned before, clunky phrases and little examples. Talks about titles, about abstracts. It has a special section on non-native writers. So it's available for free at this link. And the second is a book that has a very compelling title, How to Write Papers that Get Cited and Proposals that Get Funded. I think it's from sort of not from physics, but from I think from geophysics or atmospheric sciences. But I think the broad concepts of this book are super useful. So with this, I'd like to conclude, and I think we probably have maybe 10 minutes for questions. And thank you very much. I'm really glad so many of you are here, and I hope that we can meet in person at some point. I was looking forward to attending this workshop if it had been in person, but I'm sure that this will be possible in the next future. So thank you so much for listening to me. Have it.
Thank you, Matteo. It's really good to hear you talk. And there's some comments in the chat, but let me just mention that this is the kind of talk that is hard to literally ask questions for, but it's the kind that is really nice to make comments and have further discussion.
Absolutely,
So
yes.
let me start with something that's in the chat, which is the business of using I or we, and because it sounds so self-centered. And one of the comments is in non-Western societies, this is really looks boastful. Can you comment on that?
Well, I think, well, first of all, of course, this is sort of a detail and a nuance. If you don't want to use we or I don't think this is going to change the fate of your paper. It's one of the many details that together make your paper good or not. What I can tell you is that the solutions for not using we and I, a lot of times are not just impersonal, but they are sometimes unclear and inaccurate. Sometimes I read the sentences, this has been measured, and I ask myself, who measured it? Did you measure this in this paper, or somebody else before measured it? And you read it and it's not clear. So the fact that you're trying to hide this narcissism, it's really introducing some inaccuracy. Also, passive is longer, yeah, sometimes it's just less clear. So again, this is a nuance. I'm not saying you have to always use active. In some cases, passive is better. In some cases, you just need a little bit of variety. So anything actually that I say today, you don't have to take it as this is the way to go. This is just some thought. So of course you have to do what makes you feel confident, but I would say, you're authoring your paper, you're putting your name there. So in some sense, this is narcissism too. So by using we and I mean, it's just a sort of not a very profound way of defining narcissism. So I think that using we and I are actually not expressions of narcissism, but just accurate renditions of what is going on there. So yeah, maybe one has that feeling, but I don't think it would tell really that you're a narcissist if you're doing that. So, but again, this is a small detail. It's not a super important part. So you have to do what makes you feel confident.
Yes. Okay. Be comfortable. That's good. And I think you made the real point that being clear is most important. Okay. So I still have trouble with that, and I think for people in the Western traditions, you want to know sort of where you're on that continuum for being very boastful or down to the other end. Okay, so it is a difficult issue, and phrasing it well and making it a story. I really like that idea a lot.
Yeah. Somebody's asking for my email, so I'm going to put it in the chat. But I will also, I don't know who is going to get the slides. I say we have Michael as a raised hand.
Yeah, so if I can ask a question, maybe a bit more general in terms of communicating science. So it's very hard to write articles, but we see science being communicated a lot through talks and through like different kind of medium than just writing. And sometimes even in talks, I found that I'm able to understand better the topic just because there's more images and people are allowed to use a bit more of different context to explain their research. So I'd just like to know your opinion about how, I mean, is writing still the optimal way to communicate science, or you will see it evolving differently?
Well, I definitely see that there is space for more. People are thinking about complementing papers with videos, with presentations, with other material. I think the two things are very connected, actually. I've worked with a lot of public speakers, not just scientists, but when I was in that political setting, I was preparing speeches for this person. And one thing I noticed is that people who are giving great talks, well, first of all, they prepared. And this is something that we sometimes don't do in science. I remember preparing for my talks, and the night before I was putting together, I have 10 minutes, so I have 10 slides, and that's what I'm going to do. And I was not rehearsing them. So maybe the talks that you refer to are, people have practiced, they have thought about it, and they have rehearsed. And I see one thing that, for instance, good speakers do, they write down their talks sometimes. They rehearse them so they are perfectly on time. There was one politician who was working with, she was impressive. They would give her 35 minutes and she would finish in 35 minutes and 50 seconds because she rehearsed it to perfection. So I think the key message of both things, I think that they're actually very similar. And the great speakers that I know are also good writers usually. And the key underlying thing is that, first of all, that you are relating to a certain audience. So you're giving a talk at this conference, there are 200 people. You can imagine that most of them will be in your field, but some of them will not, and some others will be from completely other fields. And so the talk gives you the opportunity to start very broadly and to do certain things. So I think that the two things are really, really related. But as you said, there are some arguments for complementing the written words with some. Of course, it's hard to replace, some details, some sentences. If you want to go and look at the tables, the number, the graphs, it's hard to think that you can replace a paper. But definitely, every communication possibility, you should take advantage of it.
Okay, thank you.
Yes, thank you, Michael.
Okay, and are there other questions? Sorry, I'm having a hard time just following if there's some hands raised. If you do have a raised hand, please speak up.
So there's a question. Yeah. Sorry, go ahead, Matteo.
Were you referring to that in the chat about hype?
Yeah.
Yes. Yes. So the question was from from the director. Should scientists hype the results and work? For instance, this research could lead to the advent of the next quantum computer. Of course, the answer is not. And I mean, there are several reasons, but I guess a lot of times when you see scientists hyping their work is not. I mean, their intentions are not really of doing that. It's more a reflection of maybe their inexperience in communicating it. And so they think, okay, let's say I have to present this work to a broad audience, maybe a lay summary, maybe a journalist, and they will not understand the details. So let's get very broad. And using your example here, this result could lead to a quantum computer or could lead to the advent of quantum computers. And maybe your results, I don't know, maybe your result was showing that the coherence time of certain qubits is a little longer than other qubits. So I guess this is what happens sometimes to you. I talked about the hourglass, and you have to, when you talk about the implications, so the so what in this case, the advent of quantum computer, you cannot become much broader than what you started with. So your question may be, this qubits have a short lifetime, and we demonstrated the lifetimes can be made a little longer. So if you started sort of narrow, just keep at that level. So try to really, if you have an open question that you resolve, connect to that open question and be very honest. It's actually, it will not help anyone. The journalists will look at your story, say, or the public, and that they will realize that you are hyping, or they will be confused. So obviously, it's not the way to go. So try to be simple and clear, but also honest in what you can really claim.
Okay. Are there others? So I have one, two comments. You said something, you said figures. I want to re-emphasize that. That's just so important. When I read a paper, I first glance at first read the title, second glance at the conclusions, then go to the figures and try to see, now, what is the important things reading the figures, and then finally read the abstract, which is supposed to really say, this is what's in this paper.
Yeah.
Matteo, would you say that's a good way to read a paper?
Absolutely.
Write for someone else?
As you're showing, the even very expert people do that. So it is we are wired to think visually about things, and figures are the best way to communicate your results. So my suggestion that I have is, when you have your paper ready, take the figure out and try to give a little presentation using the figures. Is it enough, or you need something else? And read the captions one after the other. Do you sort of get the story? And if not, maybe you just by adding a couple of sentences, you can make the story readable just from the figures and the caption. And so I think that focusing on them as a separate element would actually be very helpful.
Excellent. Okay. Then I want to insert something else, because there's a few things that I think I've heard over the last many years that really stuck with me. One was giving a talk, but I think this probably relates to writing as well. And the our instructions, or the advice for giving a talk, is talk to the person in the back of the room, not the person on the first row who's nodding and saying he agrees or disagrees. That's not the person you're talking to. Talk to the person in the back of the room.
Yeah, absolutely. I guess this is very resonating with this idea of multiplicity that I was talking about. And again, I think you can talk to both, right? There will be some part of your talk. You don't have to forget the person in the first row, but you can start by focusing on the person in the back seats and trying to tell something meaningful to them. Use nice images, use a simple story, use the broadest possible introduction that you can have. And then, of course, there will be one or two slides where they will get lost. But if you can signal that, you can sort of say, okay, I'm going to talk about this experiment, and this is how we did it. And they get the message, okay, I don't care about this. This is going to be technical. I will just be tune out, and I will reconnect when you're doing the conclusions. So you can even have sort of cues for them that tell you, okay, now I want you, the expert, to be really paying attention, because I'm going to tell you something that actually the thing that you want to hear about, not really the introduction that you're probably familiar with. So I think that if you prepare your talk carefully, you can keep them engaged without losing any of the two types of people at the same time.
Excellent. And so that advice I read was meant to be a short sentence, that you don't ignore the person in front, but it's just so easy to get trapped into talking just to them. So I agree, and thank you very much. Are there some other questions or comments?
There's a great one from Matt in the chat. It's a long one, so maybe Matteo, you just want to read it.
Yes, I think titles are super important, and we cannot underestimate their importance. I mean, of course, if you're working in the field, you will notice the paper even the title is really bad. But for instance, I know a lot of journalists, the only thing they do to decide what they cover, they look at titles, and if they get something from the title, then they read the abstract, and if not, they don't. But also titles give you sort of a preview of what you're gonna find. For instance, there are a lot of titles telling, I really don't like these titles that tell you, say, infrared characterization of this superconductor. What the title suggests is that you just apply some techniques, you didn't learn much from them, and that's what you were trying to do. But the title should be focused on what you learned, not on what you did. And so when I read a title like that, infrared characterization, my assumption is that they will not tell you anything new or interesting. They're just telling you what they did, and probably they didn't find anything interesting. So that title sort of turns me off. And you know, as an editor, I may consider highlighting a paper. I don't even look into that because the title is already telling me there's something not interesting about this paper. Actually, that link that I was suggesting from Review of Modern Physics has a specific little paragraph on titles, and I think it's a very, very nice one to take a look at.
Good. I recommend that Reviews of Modern Physics as well. Yeah. Let's see. There's other things in the comments.
I'm not sure I understand. Amy is getting frustrated on scientific reticence. I don't know why.
I didn't raise my hand. Sorry, I'm just putting things into the chat. Well, because, you know, in metrology or in science in general, the term uncertainty has a different meaning for the general public. And so when the public hears, oh, scientists are uncertain, or, you know, we have a certain uncertainty about this climate change or this threat, I feel like, you know, if you kind of admit, I agree, it's a paradox. If you admit that you don't have all of the data, or you simply don't know, or you can't draw a conclusion, you're being a good scientist. But it becomes very difficult for the general public to think, well, you know, we've been funding this science for decades and they still don't know anything. I was frustrated with my boyfriend. I said, how come we don't know this about water? And I was thinking that about Steve's talk earlier. I'm like, how come we don't even know water? Water is such a fundamental thing. Don't we know everything about it yet? And he's like, it's really hard to know about water. So I'm a very much an outsider. I'm not in science. I'm just near science. But I do feel that it's a double-edged sword, right? It's a bit of a paradox. If you're humble and you admit what you don't know, your sort of political enemies will say, oh, they don't know anything, and we should just cut this funding. And I feel to me that's a really real problem. I even wrote the author of this Nature Physics essay, Buchanan, and I felt he was too timid in talking about uncertainty, and he agreed with me. He's like, well, looking at it now, I agree with you. I am too timid about talking about uncertainty. So you can get really self-reflexive and semantic about these things. But I will advocate, as the outsider who has interviewed a lot of scientists, it's very frustrating for the public to know what to think, what kind of conclusion to draw. We need a conclusion. Not, we need more research and investigation into this problem, but I need to know what you know now. And so, again, I'm an outsider, but also,
I can tell you as a comment about the science, I have seen this being done by some scientists, and I think that's not very useful, is when a scientist, okay, they want to be accurate. So in a paper or in a talk, they spend all the time talking about why what they talk about may be completely wrong. And of course, you want to be honest. You don't want to promise something that you cannot promise, but also, sometimes this comes at a detriment of what actually is your conclusion. They're so worried to be accurate, they don't actually tell you what the conclusion was. So all you're left with is, oh, we've heard something about it. It might just be completely wrong. So there is an excessive emphasis on what you may not know, which may be very honest, but it doesn't have to sacrifice the key message. Also, my experience is that politicians and the public are better than you think at tackling uncertainty. So if you give them numbers, they can sort of work with that. Of course, there will always be, you know, deniers and people who think, okay, you don't know anything if you you just have a probability. But I think if you use uncertainties correctly, and maybe a great guide for that is the IPCC, they have some guide on uncertainties and how to communicate them. You know, the Intergovernmental Panel on Climate Change. I think it's worth reading, even if it's not related to climate change.
Okay, very good. I think we have to end the questions and comments, and thank Matteo for his marvelous presentation.
Thank you very much,
Thanks,
Richard. Thanks everybody for being here. Feel free to contact me with questions, and I will share the slides and any information that can be useful.
Excellent. Thank you.
Goodbye, everybody. Happy to see you all in person. Have a good day.
Good.
Bye-bye.
So, Sinead, what's next?
Next is the closeout, so it's up to you. Do you want me to share the slides, or are you good with sharing them?
Well, good is another story, but I'll try to share.
Okay.
Is there anything
I
that
sent
we should
you.
say? Oh.
Sorry, I just said I sent you an updated version of the slides.
Right, and I updated yours a little bit.
Okay, great.
Good. Okay, so is there anything else that we should share now before just moving
Yes,
along?
Jingyi has a link to the survey she prepared.
Oh, yes, please. So let me know when I should.
So Jingyi, would you like to mention the survey?
Yes, I'm working on it. So here is a link I'm going to send in the Zoom chat. So, okay, sent.
Okay, please fill out that survey. It's hard to do surveys because you get asked a lot of time to do this survey and that survey, but this is important. We have funding for this with a really special opportunity, and showing that people care is really important. Are there other things?
That's it for now.
Okay, then I'm going to attempt to share and give me, help me if I have trouble. I hope I got the right one. So is that sharing okay? Sorry, is that working?
Sorry, I was on mute. From here is fine, I think, because when you go full screen, it distorts. So I think if you can just share it this way.
Start this way?
Yeah, I think so.
And you can hear me all right?
Yes, we can.
Okay, then let me go back. Okay, so I'd like to say, emphasize that it's exciting to be part of something new. And what is new? There's new opportunities and new interactions. And it's not just that we get one-on-one interactions and learn specific things. It's also awareness of research. In this case, it's in Africa and the United States, but it's really global is what's important. We've really learned something in this few years that USAfri has been going on. And we've learned that through electronic communications, that there are great opportunities for collaborations. We started with a very different idea, and we've wound up with something that gives new opportunities. And one of the things that I like to emphasize is that there's a lot of good people on each continent and on all the continents that are ready and willing and want to share and want to work with one another. And just as a reminder, a challenge is use what you learn here. That's maybe small compared to the big picture of all the ways that you can interact and work together. But the material is recorded and is available, and it can help you identify potential connections and collaborations. So here's a little story timeline. It's a story. I hope Matteo would view this as a story that's worth knowing. This started in 2010, even in 2008 to get ready for 2010. And it's not a misprint that says to 2030. This has become a series sponsored by the International Union for Pure and Applied Physics. And that gives it breadth and depth and longevity. And we're starting our second cycle. That's every 2 years until 2030. And it's what's been the backbone for building up things that now USAfri builds upon. So in 2019,
Richard.
Yes.
We need to see the second slide.
Oh.
You should move to the next slide. Yeah.
Oh, sorry, but it shows on me timeline for USAfri.
No.
Does that show for you?
I think
It's
it's
still
stuck
the
on your
front row.
first slide, Richard.
Oh.
Yeah, we still see the title slide.
Oh, geez, thank you very much. I'm not sure what's happening because
That's why I'm afraid of PowerPoint now.
Oh, okay. Well, so let me go back to then. I'm going to stop share.
I mean, you can share and press F5. That should take you to the.
Maybe if I go. Is that
if
doing
you do-
anything? Nope.
No.
Okay. It actually shares in a way that's unfamiliar to me. So let me see if I can just. I just got out of the screen. Now I'm going to share again. Okay, now I didn't want you to see that first. So now I have to. Are you seeing my screen?
Yes.
Oh, brother. Okay, sorry. Once again, I wanted to go back to
slideshow. Yeah.
Now, do you see that? And does it change to the second slide?
Okay.
Second slide, yes.
Yeah, no, that's better. Yep.
You can see it. Well, it looks the same to me. Okay, so started with 2010 with ASESMA, and 2019 was the award by the Innovation Fund of the American Physical Society. Renata is the one who figured out that this was available, and Sinéad was one that saw a lot of things that were possibilities. And I sort of went along helping them, and Omalolu was involved in everything, especially because of the new East Africa Center that he's the head of. So it was just the right moment. And at the time, it was all in person. This was the idea, was that it was a limited thing, and the workshop was going to be limited to invitation only, 20 people maximum, because you just couldn't afford travel for more people. In fact, it was really generous of the APS to provide money for travel that would involve 20 US and 20 African participants. And the idea was to initiate collaborations. Okay, so in 2020, everything fell apart. What do we do? And it took a while to figure out, well, what do we do? So 2021 was the virtual workshops, and it was getting off the ground, and I think it was just great to get going, but oh, it was that difficult to actually figure out what to do. But what we learned, and this is not we, it's a person that, like me, I'm kind of the last person to be learning and inventing things like this. People around the world and the other organizers understood better how to use virtual interactions to actually do something that's bigger than was initially proposed. So here we are at the second workshop, which had to be virtual for quite different reasons. It might have been possible to have it in person. It would have been possible to have it in person, except for visa issues. So now we've learned something, and we have to work on this more in the future. But anyway, so now, because it's virtual, we have the advantage of the opportunities and awareness that you can have by virtual and in-person interactions. And finally, we're at the step of in-person interactions that's starting next week. It's really, this is a transition point for USAfri, but we want to keep not just the people that can be involved in the in-person interactions this year. We want to keep the interactions with other people too, and build it up with for the future. Now, I hope it does that get the next slide?
Yep.
Okay, so this is a beautiful collage made by Amy Young. That's the in-person interactions for the research visits that pairs and the visitors and the host in this next 2 weeks mainly, but some that can happen later this year, and some that unfortunately can't happen this year because mainly of visa issues. So those interactions are going to continue virtual, but we really have some possibilities, and it opens the door for new possibilities. To really see this, of course, we'd have to leave it on the screen for a long time. And I'd be very happy to do that. And Amy will be happy to share this with everyone. But it's really fun to see, what's happening and to put it in a beautiful light like this figure. I think this is a perfect example for the emphasis that theoretical physics is not just equations, it's much more, and these personal interactions, virtual and in person, are very much a part of what we are doing and should do in science. So here are the people that work so hard for USAfri over the last few years, so especially if these other people on this slide, let's give them a big hand and appreciation for the work that they've done. So can everybody give them a hand, raise your hands, whatever you do. I can't see it, but I'm confident that the people on this workshop really appreciate.
Thank you very much.
Okay, and let me do the next kind of thanks. The people who made this workshop work. I believe, and I hope you do, that this workshop really ran smoothly. And we've learned a lot over the years of how to make virtual workshops work. And the person most responsible, almost entirely responsible for the program, is Sinéad. So thank you very much. And the people who that made the workshop work in the very practical sense is Amy and Jingyi. Notice I'm only listing first names. I think we've gotten to the point of knowing who people are, and being on a first name, I think, is the right thing. So let's give them a big hand as well. And I want to ask Jingyi or Amy to thank the others. I think doing it in your voice would be better than my voice. Can you unmute and mention the other people that have helped so much?
Can you hear me? Okay, thank you. So I'm going to thank all the workshop helpers, Zoom helpers, Sostrin, Chenxing, Sunday, and Hongjing and Xizhang. Thank you all so much, and Hongjing. Thank you all so much for coming and helping us to run this Zoom meeting. Thank you.
Good. I personally was helped by Hongjing, and I'm sure every one of you that gave a presentation was helped by one of these people at least. So thank you very much. And lastly, I want to credit the people who make this possible in a financial sense and more than a financial sense, and in a way of helping promote and disseminate the information and making this work out. Of course, the APS Innovation Fund is the one to help to thank most of all, because they really made it possible and provided funding. So I just want you to appreciate the support that we have. And I think that's all I want to say, except I'm going to I want to turn it over to Sinéad and just for anything, this last words, and to see if some of the other organizers want to add some words. So thank you to everyone that's involved and everyone that's participated. Thank you. Okay. Oh, I'll stop sharing.
I think we were going to leave you with the last word. Renata, did you want to say anything else? Or Omo? Renata, you're on mute. No, Omo. Okay. Renata, you're still on mute.
This was a wonderful meeting, and we hope to continue in a different mode starting next week. Welcome to New York City, and then to other places in the United States for those who are coming. And for those who are not, we will be streaming, we'll be in Zoom again next week for the electronic structure workshop here at the International House and Columbia University. So I hope to see you again next week, participating online in this workshop. So I hope to see you soon.
Thank you.
Omo? Do you want to say something?
He said no.
He's a very important part of this. And Omo, are you on? Okay,
he is.
Well,
he is. He's very shy, you know, Omo. So.
Oh yes. We'd love to hear
Until
your
next
voice.
week. Until next week, folks.
Yeah,
there is more. More is coming.
Bye,
Okay.
everyone. I think are we gonna leave the room open, Amy, for people to talk or no?
Yes, Jingyi, we'll leave this room open, and
Okay.
I will also sit here if anybody has questions or needs some assistance. But I posted the link to the YouTube live stream, and it will also be archived at the same place. And she's made a playlist for the day 1 and day 2, so day 3 is still running. And also, if anybody, I guess Matteo can send me his talk slides. I will link them from the workshop webpage. And for all of the current participants, the videos that of the pre-recorded videos of the 10 and 20-minute research presentations are also linked from that page if you miss something, but you will also see it on the YouTube recorded live stream. And just a reminder, also in the chat, and also on the homepage of this workshop is a link to the workshop for next week. So if you're interested and you would like to register, the registration page is still open for the virtual participation, and that's free. So just remember to scroll down to the bottom and use the code FREE, and you'll be able to access those talks virtually as well. So there's plenty of things to look forward to next week, and we'll also stay tuned for Matt Horton's school and see if it might happen. That will be great. Yes.
Okay, and thank you for making the website so attractive and accessible.
Okay, I hope it'll be better. I still have website updates to do, and but I was really happy to see. And there's Anne Justine, and there's Amisi. So I'm very glad to always see your face and to meet new people. So we're very interested to hear from new people. So don't be shy. And we know that's, we don't want to. We want to be sure that everybody who wants to be involved is welcome. So,
Okay.
Arinala, thank you. And Isaiah, I hope that you made some more connections for the people you know in Nigeria and people outside. And thank you, Andres and Fatima. So we'll say goodbye and let everybody get some hot tea or water. But Jingyi and I will stay here. Okay? So thank you so much.
Okay. Thank you,
Okay.
everybody.
Bye-bye.
Bye-bye, everyone.
And good to
See you
see so
next
many
week.
good
Bye.
faces. Yeah.
Who is Samsung Galaxy S7? I see the picture, but I don't have the name. Yes. Yes. I'm going to ask you to unmute yourself. I answered, hi, Umaru. Also nice to see you. Oh, there's Georgis. Yeah, I'm going to take another screen capture so I can include you in my overview video. Yeah. Okay, great.
Thank
Oh,
you.
there's Emmanuel. Nice to see you, Emmanuel. Hi, Oluk Benga. I hope you got some good questions. Yes. And oh, there's Winfred. Very nice to see Winfred. Nice. So Winfred, I'll see you week after next because you'll be in Urbana, right? Or 2 weeks. I will see
I'm coming
you
tomorrow.
to Urbana tomorrow.
No, to
New York.
New York.
Yeah, but I'll see you when you're in Urbana.
Okay.
Yes. And there's Emmanuel. Yeah, and I'll see you and Ibrahim when you're in Urbana and with Aleph. And also I would like to meet with you when you're here and also with André Schleife. So I think you should also say, you'll want to meet André there too when you're in town. He'll be in town for half of your trip. He just told me today. Hi, Emmanuel from Tanzania. It's nice to see you. I haven't met you before, but I'm glad to see you. And I believe I answered your question, right? So you had asked about the talks. So I put the link in the chat. Jingyi's live streaming them, and also I hope she'll chop this part off in the final. But yeah. So good. I'm glad that you found some talks useful. Umaru
Recording
Garbawali.
stopped.
Haven't met you before, but we're happy to see you. And because I never go to the summer schools or SESMA, so I actually don't know. You might know everybody, and I'm the one who doesn't know anybody.
So myself, I'm here in the University of Rwanda College of Science and Technology. I'm the Dean of the School of Engineering.
Oh, great.
Yeah.
Nice to meet you. Have you been to the SESMAs or the USAfri workshops before?
No, this is the first time.
Well, we're happy to see you. I hope you found some of the talks useful and some ideas
Sure,
for connections.
I attended today, but I really enjoyed it.
Great.